meant to do that beforehand. Oh well, it's all in there from yesterday. Okay, so let's talk about networking again, which is good because I think, like I said, this is one of the harder topics. So it's good that we're actually going to be able to touch on it twice. So I'm going to review what we talked about yesterday. You're going to interrupt me or stop me at any time. And you're like, hold on. We need to get into that a little bit more, Michael. Okay. So networking between the containers in a pod, the pods themselves, the pods across hosts, the hosts, and of course, how the cluster talks to everybody else, and then how the cluster interacts with services. That's all really the focus here. Mainly it's the Kubernetes, the EKS components, but that's all part of the focus. And so what we did yesterday is that we actually started talking about the fundamentals of AWS networking, which at least at a base level, you have to understand to really understand how EKS is going to function. And of course, we talked about how, every account by default can carve out 5 virtual private clouds or VPCs, which actually have networking information associated. When you go to create one, it's going to ask you for networking information. So in this case, down here in the lower left-hand side, it's a 192.168/16 network, which means those first 2 numbers don't change, right? And then what happens is that the subnets that are actually put into availability zones, because subnets cannot span availability zones, at least not as of today, they are a sub-slice of that big VPC pie that was defined in the lower left-hand side. So notice that the first 2 numbers in the subnets never change, but that third number does, because this is now a /24, which means that third octet can actually change to define the subnet network versus the overarching kind of network itself. And I said that that last number ranges from 0 to 255, which technically would give you 256 possibilities as far as like IP addresses available for your hosts. But the first and the last number are typically taken by networking to say this network versus everything, broadcasting on the network. And then I said that if you included those 2, Amazon takes a total of how many IP addresses off every subnet. Does anyone remember yesterday I said how many IP addresses does AWS take off of every subnet? So if this can run from 0 to 255, and I've lost 0 and I've lost 255 because that's basic like IP networking.
Isn't there like 3 that AWS takes?
Exactly. It usually takes 1, 2, and 3 in the subnet, whatever the first numbers are, like 1, 2, and 3 typically, right? So you're going to lose 5, right? The first one is typically for routing. The others are actually for DNS. They say they're reserved. Sometimes they say that number 1 in the documentation is DNS. Regardless, they're going to take 3. One of them is for DNS. Another one is actually for routing, right? So AWS is going to take 5 IP addresses. Now, the other things that we were looking at or thinking about yesterday was what makes something a private subnet versus a public subnet. The difference is whether you can route to the internet directly or not. That's the difference. Because remember, by default, all of these are private networks. They all have private IP addresses. Why? Because they're in your VPC, which you gave a private IP address. What defines a private IP address? It's RFC 1918. Basically says, 10 dot whatever addresses are private, meaning they're not routable across the internet. 192.168 addresses, those are not routable across the internet. And then I think it's 172.16 and 172.31. That range between 16 and 31, might be 32, I'm just drawing from memory. But like those ranges are not routable across the internet. So typically if it's a 172 address, a 10 address, or a 192 address, it's not routable across the internet. There are specifics actually underneath those. And that kind of like most people like have trouble wrapping their heads around that because you're like, Michael, you just said it wasn't routable to the internet. You didn't say it wasn't natted to the internet. Yeah, natting is what we do at our house. We have a 192 network at home. It hits our router, and then the router acts on our behalf as a proxy. It has a public IP address, and it goes and grabs the information we've requested and then brings it back to us. But the internet doesn't have the ability to get directly to us, of course, unless it gets past our firewall. But there has to be some address translation because we don't have public IP addresses that are available on the internet. Like in our house, we're not assigning my phone, my computers, we're not assigning them public IP addresses, which would then route across the modem to get to the internet, which means the internet could potentially route across my modem back to me. That's not happening because we're running private networks. And so in a private subnet, the condition is the same. You're not actually giving it a public IP address. It's using one of those private 192s, the 10s, or the 172s. And so we need something like a NAT gateway, which acts like our cable modems or our home routers, which is going to act on our behalf, translate our private IP addresses into public so that it can then go and be an ambassador for us, grab information and pull it back. Now, a public subnet is a little different in that you can see the NAT gateway is sitting there because what's happening is that we would give the NAT gateway a public IP address. And by doing so, we allow that NAT gateway to route across the internet gateway on the right-hand side, and it can route and talk to the internet, and potentially the internet could talk to it. But just so you know, NAT gateways typically don't allow inbound traffic, right? You can initiate outbound traffic, but they don't allow initiated inbound traffic to it typically, although it does vary. So the key, by the way, to being able to talk to the internet is to basically have a route table that allows you to route to the internet. So the ability to go through the internet to get to here. And you have to have a public IP address, at least in addition to your private IP address. So you need to have a public IP address because then that way you can actually get through the internet gateway, which is just a router really, and then get out to the internet. Without a public IP address here and a route to this, and of course no firewalls. Right, there's firewalls here, that's not going to work either, right? But without those two options of an IP address and a route to the internet gateway, you can't get out to the internet. You say, Michael, that's pretty cool, right? So here we are. By the way, here's some route tables. Route tables are maps that says, hey, if I'm looking for a 1962 network down here, I want you to just, right? Looking for a 1926 work down here, I want you to just go local because you're on that network, right? So just talk locally. It's actually here, right? And then obviously, if you want to go somewhere that's other than this, because this is the only other entry in the route table, then you need to go talk to the NAT gateway. So you're over here and you're like, hey, it's not one of these networks. Let me talk to this guy. Who then's going to take the information. He's going to talk to this guy. And this guy is going to go out to the internet, right? And the only reason the NAT gateway can get out to the internet, this guy right here, is because it has a table that says, hey, if it's not local traffic, then I'm going to go out and talk to the internet gateway. If I don't know what to do with this, I'm going to send it to the internet gateway. That's what the public subnet route table says. The private subnet route table says, if I don't know what to do with this, I'm going to go talk to the NAT gateway. And that's just like basically how AWS does it. By the way, excuse me, NAT gateway is a service that you can run. You can also run your own NAT gateways. They're not nearly as scalable. This service came out like, I don't know, 6 years ago or 7 years ago and made NATing inside AWS a lot easier. Something to be mindful of, if you're in your own personal account and you start a NAT gateway, it does charge like a penny per hour. You might not think that's a big deal, but then it does start adding up, right? When you've got 3 or 4 of them running. So just something to keep an eye on. And then we talked about firewalls past the routing components, how there's a stateful firewall around each network card that's attached to either a virtual machine, a Lambda, an S3 interface, like a virtual endpoint, for example. And so there's basically this firewall here called a security group. Firewalls by default block all inbound and outbound traffic if they don't have any rules in them. But when you set them up, they allow all outbound traffic and they deny all inbound traffic. So just so you know, just because you give something an IP address and put it on the internet, it's not going to get past the firewall in terms of an inbound traffic perspective. So it's recommended, by the way, that, you only allow in the ports, the specific ports and protocols that you're interested in. And this can be IPv4, which is what you see on the top of this inbound rule here, or it can be IPv6, which is a whole different beast when it comes to IP addressing, because pretty much every IPv6 address is internet routable. There's some exceptions there. We're not going to dive into those. I mentioned yesterday that there was another subnet firewall that's stateless that isn't really touched unless you're typically going to deny IP traffic. Does anyone remember the name of that stateless firewall that wraps around a subnet, not around a virtual machine? So that would be network access control lists. Those are stateless firewalls that operate around a subnet. So they would actually wrap around like this particular piece, right? They wrap around the subnet itself. Typically, Amazon just has them set to wide open because messing with security groups, firewalls, and network access control list firewalls can be problematic, just in terms of getting things aligned, right? But people do use them to deny IP addresses. And then we talked about just DNS, how everybody gets a private DNS name, which is why one of the IP addresses is taken off of your subnet range, because there are resolvers all over the place at AWS. And then how, when you assign an IP address, you then get a public DNS name, right, with the public IP address, which is, by the way, usually your IP address with dash, like EC2 dash your IP address, then your region, and then compute.amazonaws.com, right? So just know that actually is also true for your internal as well. It's just a different domain name. And then we started to talk about container to container, pod to pod, and kind of ingress to cluster communication. But I want to stop there. Is everyone good for us to move forward? Were there any points of confusion that need clarity or anything to dive into there? No? Okay. Good. That's excellent. Okay. So I mentioned that when you're just inside a pod, you've got multiple containers in there and they need to talk to each other. It's just localhost. It's a loopback address. And you're just talking to the port that's bound to the loopback address, because Kubernetes does, in a sense, treat that pod as, at least from a networking storage perspective, as if it's kind of a virtual machine, right? It kind of namespaces it to this all together, right? And so in this particular case, if you need to talk to, if you're an application and you need to talk to port 8443 because that's what your Nginx application is listening to, you're just going to loop back up to those ports. You don't need to specify an IP address or anything like that because you're sharing the same networking stack. Now, notice in our ETH0 here, this pod is actually assigned an IP address from one of our subnets. It's got a 1. Notice this little blue private 168.1.0. It's got a 1 on it. It's a 192.168.1, and it's got a 194 address. Notice that the host IP is actually a 192.168.74.100. I find that interesting, just noting the distinctions. Because I'm like, well, what subnet is that on, right? Kind of curious. So as we move on, because this is all intra-container, like intrapod, communication. How do the pods talk to each other outside of the containers and the pods? Like, how do the pods talk to each other? And it's all in the same host, right? Well, the cool thing is that the node, the host, actually has its own namespace. And so in this particular case, if pod A is looking for pod B, what ends up happening is that they actually have IP addresses, but they can just like virtually tunnel out to each other, right? So that way there are routing tables set up for each namespace. So each namespace has its own routing table for how things can find each other. And so if pod B is looking for pod A through like a DNS name or an IP address, it knows, hey, go ahead and run it through here, right? And so, for example, at the host level, and let me clarify that as much as I possibly can, because I want to make sure that's clear. This pod, when it's looking for something, is actually going to go out this interface. The routing table here is going to say, look, any traffic that you're looking for, just go ahead and send it. Hold on. Any traffic that you're looking for, just go ahead and send it out through this interface. So just send it out through here, right? And then what's going to happen is that the routing table, when it hits this, because it's going to go directly to the host interface, the virtual interface, if you will, that's attached to the host space. In the host namespace, there's a routing table here that says, look, if you're trying to get to pod A over here, I want you to go talk to this virtual interface. And so it's going to route over to VETH0A. And then immediately it's going to kick it right into this VETH0B kind of virtual interface, if you will. And then it's going to talk directly to the pod. So the routing tables over here and here at these different like namespace levels, this is what's enabling traffic to route. All of this is set up by Kubernetes, by the way. So all this is set up.
So if those two pods are different namespaces, does it work? Can it communicate?
Yeah, so if the pod's in a different namespace, let's say that these guys are separated, then what would happen is that pod A would actually just point towards like whatever virtual interface, because it doesn't really matter what namespace like pod A, for example, is actually in, because once it gets out to the node level out here, this particular routing table will tell it what virtual interface to talk about, and then its sub interface will actually go to whatever namespace it's in. So this little space right here between these two namespaces, this is where it does the namespace jump from the host namespace, like the node namespace, to whatever namespace it's in. So it doesn't matter what namespace it's in. This translation right here between VETH0B and VETH0A is going to go into whatever namespace that pod's in. And the reason it does that is that way it can actually keep this virtual networking device, this VETH0B, it can actually keep it associated with the pod in whatever namespace the pod's in, as long as the host knows how to get to it, which it does, because the virtual interfaces here at the host level and at the pod level are always linked. So it can chase the pod no matter which namespace the pod's actually in, because the host always has a portal or a link between the pod's virtual interface and the host's version of that interface. Is that working? Are we good? Questions? Okay. So just remember that like whatever networking interface the host has assigned to the pod, it always has a corresponding interface at the host namespace versus the actual namespace of the pod itself. So to speak earlier, like Rama, you can kind of see then what if you have 100 of these pods, why all of a sudden there's some strain on the operating system, because it's now having to create all of these virtual interfaces, 2 of them at least per pod, to make sure that it has a host like portal to wherever the pod is in whatever process namespace it's at, right? And so this is why things can get a little squirrely from a performance perspective around adding more than 100 pods. You just have to experiment and make sure you can handle it.
Right.
Okay. So that's just within a single host. It actually gets a little easier, like, because like in this sense, for example, this pod to pod communication just happens like within this kind of like VETH tunnel, if you will, right? In other words, notice that it never actually touches, if we go back to our previous drawing, it never actually has to go through the host interface. It never actually has to hit, if you will, it doesn't have to go out the networking stack of the host, right? Because it's in the node, right? It doesn't have to leave. So looking at this from just a slightly different perspective, what happens is that each pod on a node that's in a Kubernetes cluster is VPC aware, meaning it's aware of the subnet. So the pod is going to get an IP address, and so are the virtual tunnels that it's connected to as well. So pod to pod communication is going to happen through these VETH tunnels, and they're just going to talk directly to each other. But I do want to point out that these VETH tunnels are the linkages back to the pods, right? Because in a sense, this ETH0 that's listed here is actually just the virtual link between VETH1A and VETH1B. They're just now named slightly different. So, by the way, these virtual Ethernet names, when using EKS, they're actually not. We're talking about them as if they're virtual Ethernet tunnels because they are, but the actual name inside the operating system starts with ENI, just to be clear, right? So you might not actually see these particular names if you decide to go peel back the networking on a host, but we're just using these abstracted names because they're easier to talk about than the ENI letters, right? Because it's like ENI 833, ELAI 1, or you know, ENI 844, CVC 22. It's like the names are long, right? So here we are, and this is just a rehash of what we were looking at before. Note that this pod has a 195 address. This pod has a 194 address. This host has a 174.100 address. But note also that these pods are also attached to that network interface. So if someone says, hey, I'm looking for 192.168.1.195, this network card will accept that traffic and route it up to the pod in question. So note that the network card is actually listening for not only the host, for traffic for the host address, it's actually listening for traffic for any of the pod addresses. So you might have up to 100 IP addresses stacked over here on this single network adapter. And it's just listening for all of the pod IP addresses plus the host address. Follow me? We're good? Okay. Now, what about interhost? What about pods on other nodes? Well, here's the cool thing. So CNI, the container network interface, right? The CNI plugin for Kubernetes, to be specific, is Amazon VPC CNI. It's actually listed on Kubernetes page, right, in their documentation, along with Azure and others, right? And so what this is that this is a VPC aware network plugin, right? And so what this is doing is that when you need to talk to another system, another pod, if you will, like let's say it's 2.194, well, if you're coming from this guy, you're just going to go out your virtual interface, hit the network card. You're going to, by the way, you're going to be checking routing tables the entire time. Routing tables are going to be checked at every single step. And the routing table is going to say, oh, you're looking for that guy. Well, we're on the same network, so just go talk to this network interface. And then once it hits the network interface, it's going to pass it up the stack and it's going to talk to the pod. Why? Because you asked for this target. And it knows where that target is. So at this point, once you're outside the host, normal networking rules apply. And the cool thing about them, the way they're doing this, because there's cons to this, right? They're now pulling IP addresses off of the VPC, which, as you can imagine, unless you have 65,000 available IP addresses, that could get pretty costly pretty quickly. Which is why, by the way, you make your VPCs as big as possible, and you make your subnets, especially your private subnets for this kind of thing, as big as they possibly can be, right? Because imagine if you had 500 hosts, they're all running 100 pods. The next thing you know, right, you've got 50,000. You've got 50,000 pods. By the way, most people don't do that. So that's very unusual, right, to get to that size of deployment. But I'm sure like Google does, for example. But most of us aren't going to be running into that scale, so we don't have to worry about that as much, right? But just note that once you leave the host, it's just pure networking routing at that point in time. There's nothing fancy. because each pod has its own actual workable IP address. You can actually get just straight from pod to pod because Amazon treats the pods as if they're virtual machines. They get their own dedicated IP. And so if you're looking for another pod, you just go for the IP address of the pod. That's it. And if you're inside the cluster, you can literally just use the DNS name and it will resolve out, right, to the pod in question, and you just go right out to the IP. That's it. So it's real easy in this space to communicate. And again, just the con here is that just make sure you have a large enough amount of IPs, right? And that pops up a lot in migrations that I've done in the past. Okay, so that's it. So that's pod to pod. I'm sorry, that's container to container inside of pod communication. That's pod to pod inside of a host. And that's pod to pod on extra hosts, like right between different hosts. Any questions before we move on? I want you to know, and please interrupt me if you have a question. I want you to know because I do like, I like to make sure that you leave with extra stuff because this class just gives you a primer, right? You have to reinforce this and do it again and again and again to make sure you really at least get even an intermediate understanding of this. I remember I showed you yesterday the EKS workshop. One thing I want to point out, oh man, the things the things I find out there with Amazon, like, come on guys, you gotta do a better job of publishing this stuff. If you look down on the lower left-hand side, there's an EKS networking shop at the EKS workshop. It's AWS I'm going to post this in here just in case you want to keep this. This, by the way, will walk you through all the different styles and types of networking. So if you ever want to get hands-on with this, which I highly recommend, of course, we have a lab to do with this as well, right? But just note that let's see, if you're doing a COPS cluster, this will walk you through, for example, container networking basics. You actually see this in action, right? If you actually want to go through and work this whole thing. There's also, you can obviously create a cluster, which we've done before, but then you can actually walk through some pieces around EKS networking. So you can review your cluster and then talk about pod configuration, pod networking, and then run some interesting kind of challenges. And then you can actually run through COPS networking, which COPS is a tool for provisioning clusters inside of AWS. They are EC2 clusters that are not related to EKS. They're just AWS clusters, right? So, and then you can actually see and understand the packet flow between pods and pods, just outside of EKS as well, right? Just to see how that functions. So anyway, this is going to be included in the links I send you, with the videos and stuff. So don't worry. If you didn't grab the link, which I highly do recommend that you do, I'll actually send you a list of all the hands-on lab trainings that I recommend you look at from an EKS perspective. Okay. We're moving on to how do I allow stuff to get into my cluster? Or how do I even abstract away all the different replicas that I'm running? So I'm running 10 replicas, right? How do I distribute load across them, right? Any questions before we go forward? Okay. All right. So here we are. And these are the 4 types. I think Jarvis and I were talking about it and you heard me rattle them off. The 4 types of Kubernetes service objects. This is a service. This is an object inside of Kubernetes that you create to be able to, in a sense, expose your pods and their replicas out to either other systems inside the cluster or outside the cluster. You're like, Michael, hold on, wait. One of these is for internal use only? Yes, one of these is for internal use only, just to make sure we're clear. But the weird thing is, just to say this, is that when you use the ones that are external, it actually uses the one that's internal in order to distribute across the entire set of pods. So it's really interesting. Not necessarily complicated, but there are layers of abstraction here, right? Okay. So when I was talking about these before, The one that's internal, that's only used internally by the cluster to distribute traffic to all of the pods in the cluster, is cluster IP. Do not be fooled, because in every other clustering system I've ever seen, ever in the history of my 25-year career, when it says cluster IP, that is something you hit externally that actually distributes across the entire cluster. Well, guess what? That's not true for Kubernetes. Kubernetes likes to be different. And so here, when you use the cluster IP, it is actually for internal use only. You cannot hit that outside the cluster, which is, I gotta say, one of the strangest things. Because if you run an Oracle rack cluster and you get the cluster IP, guess what happens? You get to hit the rack cluster, right? If you're running, SAP cluster, right? I mean, pick your poison. WebSphere, like pick any cluster you want. If you hit the cluster IP, you hit the entire cluster. Well, nope, not with Kubernetes. That's not true. Cluster IPs are internal use only, so you cannot come from the outside in and hit the cluster IP address. Hopefully that's clear. Now, that being said, you can bind on every single worker node in the cluster. You can bind a single port. So let's say it's 32,000, for example, right? You can say, look, if someone comes in and hits any node in the cluster on this port, I want you to go to any of these pods. Now you might say, Michael, how does it know where all the pods are? Okay, so just to say this. Oh, this is so strange to even say. When you come in and hit a node port, let's say it's, and I'm drawing on the screen right now, right? And it's 32,000. Pardon my bad writing, but writing with a mouse is actually surprisingly hard. Let's say you hit 3200 on the node port, right? Oddly enough, what that does is it actually redirects to a cluster IP address, which then hits the pods in question on the nodes, right? So like it actually redirects to the pods in the cluster, right? So a node port just binds a port across any node, like worker node, in the entire cluster. Same port, by the way. So you got to watch out for port collisions, just to be clear. But it binds a networking port across all of the nodes. And if you hit that port on any of the nodes in the cluster, it's going to redirect to a cluster IP address, which is then going to distribute across all the pods, no matter where the pods are in the system. That's for node port. Node port does require you to bind to a port, and you do actually have to then hit a particular node IP address and that port, and that is accessible publicly, which means someone can come in and hit the IP address of any of the worker nodes on that port, get redirected to the cluster IP address, and then hit the pods. So you'll actually, it does, like in a sense, like load balancing and load distribution for you. Everyone following me? Node port links to cluster port, which hits all the pods. Right? So
Yep.
node port hits cluster port. Sorry, go ahead.
No, that's the same, yes.
Okay, good. Thank you, Ronald. Okay, now, so cluster port's private only. Node port exposes everything out by binding a port across all the hosts. Then what's a load balancer do? Well, a load balancer is interesting because this can be an external or an internal object. So for example, this load balancer could be running as a pod, like Nginx or F5 or whatever, inside your cluster, or it could be outside the cluster. But what this does is that this load balancer gets a single IP address and port, but it gets its own, by the way, gets its own IP address and port. So the load balancer gets its own IP address and port, and that's true whether it's external or internal, right? And then what happens, right? So, and this is where it gets even weirder, right? The load balancer actually hooks, oh, let me remove some of these drawings because that's going to be confusing. The load balancer actually talks to a node port that you can't see that's bound randomly against your entire cluster, which then in turn talks to a cluster IP, right? Which then in turn talks to the pods. Does everyone now believe me when I say this is why networking is harder inside of Kubernetes, just in case you were wondering? Right, does this make sense now? right?
Yeah.
Yeah, these things all chain together. So consider this also. This is using the host port of the actual machines that are being hooked into, right? This cluster IP, right, is an abstracted IP that's just sitting on top of all the nodes. So it's an IP address that's also associated with the hosts, right? And this is in turn pointing to the pod IP addresses, of which there is a singular IP address for each pod. So imagine this. You're hitting an IP address. It's routing you to a cluster IP address across all the nodes, one in particular. And then in turn, it's then routing out to the pod. So there's this layers of abstraction with networking that are happening, right? That is happening with the load balancer getting its own IP address as well. So load balancer IP address, then to the node port IP address, then to the cluster IP address, then to the pod IP addresses. You know, I'm kind of making fun here because it's good to understand this. I don't think you could make that actually more complex. Well, I say that. Let's not underestimate our ability to make things complex. Actually, let's not do that. We could make things more complex. But does everyone follow me? So every system leverages every other system. So cluster IP is the base networking component. Node port uses cluster IP. Load balancer uses node port and cluster IP. And as you can see there, external name actually uses cluster IP. I just haven't talked about what that is yet. Okay, any questions about the load balancer to node port to cluster to pod chain? Because we're actually going to talk about each of these again. We're going to make sure we drive it home. One thing to mention is that external name, by the way, hits a cluster IP, which resolves to DNS internally on the cluster. Sorry. And then that returns a CNAME. It returns a DNS name of like, hey, go here, right? Like if you're talking to an external database, external name goes to a cluster IP and then that returns a CNAME, right? Which is just a DNS name. That's all it is. Wow, that's a horrible spelling for CNAME. Moving on. So let's talk about these again, just to make sure you've got them in your heads, right? All right, here's cluster IP service. Notice I talked about all that in the abstract before I showed you this complicated picture. Okay, whew, there's a lot here, so just bear with us for a second. Okay, so starting in the upper left-hand side, an IP address was created by the API server, right? And this is in the control plane. And the kubelets, by the way, and kube proxy in particular, because remember, kube proxy is responsible for all this crazy networking stuff. It basically binds. Now see how it says 74.99? This is 74.99. This is 74.99, right? It basically says that if you're looking for these targets over here, you need to go over and talk to this 99 address. Notice that every single node in the cluster gets this update to their networking routing table. It says, look, if you're looking for 2.194 and 2.195, I need you to go talk to 74.99. That's the host that currently, well, that's the IP address that currently has it, right? And then once it hits those targets, it's actually going to route through the host, right? But remember, every pod has its own IP address, like it's a virtual machine. So if you just say, look, I need you to go talk to the pod, it's going to run through the network and just find out where the pod's at. It's not a big deal, right? And so in this particular case, the routing table on the host has all been updated to say, hey, this is where, these are the IP addresses you want to talk to if you hit this cluster IP address. You gotta grab one of these and then the next one and then the next one. So if this web app over here is trying to get to this cluster IP, like this one right here, what's going to happen is it's going to run out through the host interface. It's going to go talk to wherever these pods are located. It's going to hit the host interface right here, then talk to the virtual interface, and then hit the virtual interfaces for those IP addresses. So in other words, when you've got a cluster IP address, It just has a routing table and says, hey, go talk to these pods in order, right? Go here or here or here or here or here. This is only accessible within the cluster because it's being given, right, a private IP address, basically. By the way, this is all done through IP tables mainly, right? It creates an IP table. It's like almost like a redirection rule to redirect the cluster IP to the appropriate pod IPs. So this is great, by the way, when you want front-end services to talk to back-end services. If you just need to find your database, for example, right? So cluster IPs are internal only. Okay. By the way, I just want to note that this is a service. All of these are service kind. These are all service types, right? They are defined here when you put type in the specification. By the way, you do have to define what your app is. This selector needs to match whatever the name of your app is. If this selector is off, it's going to pick the wrong application or no application. Notice that you've got name, protocol, port, the target port on the actual system. So this is the port it's going to listen on. Target port is the port it's going to target. And then notice it's got other ports, another port definition here as well, the protocol definition. But this is actually super important, is that this selector needs to be accurate for the app that you're targeting for this particular setup. Okay. Any questions about cluster IP? No? Good. I like to go slow on this to make sure you got it. Okay, let's talk about node port. Node port is interesting because here you've got your control plane, right? The API server, and you've created this node port service that is basically listening on port 80 and it's pointing towards the target port. Now, what ends up happening is that kube proxy is updated and says, hey, if you're looking for this particular port combination, I want you to redirect just like you did with cluster IP. I just want you to redirect over here. You might be like, but Michael, hold on, Michael, wait. That front end is 32001, and we're listening on 80, right? Yeah, no, it's true. It is listening on 80, right? So it basically, a randomly chosen port is actually chosen on the local node. And then basically, kube proxy updates the IP tables rule. If it hits that node port and port combination, it redirects it to 32001, which in turn redirects it to 9376 in this case, right? Because these guys are over here at 9376, right? And so when a request comes in from the internet, it's sent to a single EC2 instance on the specific port, because that's what you're doing is with node port, you have to target a port in the cluster. And by the way, you could put a load balancer in front of it and just say, hey, hit any of these guys if you wanted to. And the front end service in this example is going to listen on port 32001 and load balance the requests out, right? To 9376 with a target of port 80, right? Like if it hits port 80, it hits 32001, and then it's going to go hit 9376. So this is external traffic coming in. Now the cluster IP, by the way, is in play here, but we're not going to peel back that translation, but it is here. It is in play. It is in play here. Here, by the way, same thing. We're defining a service. The type is node port. Notice the selector is once again a web app, right? And it's supporting port 80. It's defining a target port, and then you can define the port that you want bound to your nodes. You cannot bind duplicate ports, as you can be aware, because you're going to get a port collision otherwise. Okay. Any questions about node port? You got a 80 redirection to a 32001, and then it goes over to 9376. So just so you know, there's a cluster IP here that's actually listening, right, on port 80 and redirecting. So they don't mention that, but there's cluster IPs in play here doing that listening. Okay. All right, then let's talk about load balancer, which is the deepest one in the rabbit hole, right? So in this case, the load balancer type, in a sense, extends the node port service by adding a load balancer pretty much in front of all the nodes, right? So like in EKS, this means that Kubernetes is going to request a load balancer from Amazon and register all the nodes with the load balancer. So this is going to be an external load balancer if it's on Amazon. If you have a load balancing service like an ingress inside your cluster, you can use that as well. The load balancer does not detect where the pods are for a given service. It doesn't register the actual pod IP addresses as targets. It just registers all of the worker nodes. So all of the worker nodes are added as backend instances in the load balancer. And so by default, unless you specified otherwise, it is actually going to use a classic load balancer, but you can actually easily specify an ALB to specify it in the version. And there'll be a classic load balancer in front of all the instances, like listening to the requests, right? So the load balancer is then going to route them to the nodes through an exposed port on the load balancer. And you can add an annotation certainly if you want to change it to either an ALB or a network load balancer, if you are familiar with the different load balancer types inside of AWS. So when a request comes in from the internet, it first hits that load balancer on the lower left-hand side. It then is going to forward the request to some round robin or random, basically EC2 instance on the specific node port. And then this in turn is going to load balance it back to one of the different, like in this case, web apps, right? And once again, IP tables is here doing its thing, right? So just know that the cool thing about a load balancer is that you are offloading the distribution of traffic onto that load balancer itself. If it's internal to the cluster, it's on those pods. If it's external, like Azure, Google, in this case, AWS, it's going to use the AWS load balancer. And that's the load balancer service. Same thing here. You just change the type to load balancer, but notice you don't need to define a node port. When you define the type as a load balancer, Kubernetes will take care of all that for you. It will set up the node port and the cluster IP address for you. You won't have to mess with that. So the next time you start a load balancer, by the way, it might be interesting to see if there's any other objects inside of Kubernetes, like a node port or a cluster IP. Most of the time, by the way, you can only see, anyway, I'm not going to get into that, but like you can only see the load balancer object. Any questions about the difference between a cluster IP, a node port, and a load balancer, whether it's internal load balancer or external load balancer, and the relationships there?
I'm going to ask a stupid question here. Since Kubernetes already has its own load balancing capability, I'm trying to understand the benefit of creating your own load balancer within Kubernetes.
You can get better and more advanced redirection capabilities. For example, you can terminate SSL. You can do a bunch of stuff there that you can't do with like node port versus cluster IP, right?
Okay.
Right? A load balancer has far more capabilities than the node port and cluster IP objects, including redirection, rewrites, all kinds. You could insert scanning in there. You can do pathing, external redirect. Like there's all kinds of stuff you can do with like Nginx has, for example, one of your load balancer control versus like the cluster and node port setups. So,
okay.
Yeah, and the other thing is running an internal one. I agree. By the way, right? I wouldn't run an internal one. I would definitely run an external one, right? But I've also, like, if I'm going to terminate SSL, I'm going to terminate it external outside the cluster anyway, because I'm trying to offload those needs off of the cluster and not put them on the cluster, because then they start taking resources that I want to save for pods, right? So don't get me wrong. I agree with you. In general, that's not my preferred method. I prefer to externalize the load balancer and let another engine, another compute engine or networking engine in this case, eat all that horsepower instead of having my cluster deal with that. But there have been DoD situations where like that's not possible. It's like, nope, you're gonna run. I need F5 or God, what were we using? It wasn't Blue Code, it was something like that. Anyway, and it was like, nope, we're gonna run internal. I'm like, okay, cool. Those are your requirements. Good. Other questions? Okay, so Kubernetes ingress objects, by the way, for example, here's some pathing to like /nginx or web app. These enable you to basically reduce the number of load balancers that you use. An ingress object basically exposes routes from outside the cluster to your services via like defined pathing and traffic rules. So you use ingress controllers, which fulfill the particular like rules in question and requests. And these actually usually run through a load balancer, like an F5 or an nginx. So this is kind of the dovetails nicely, January, for what we're talking about. But by using an ingress object controller, you can transition from one like load balancer service to another load balancer per ingress or route to multiple services and do a bunch of things that you normally can't do just with node and cluster IPs. So traffic can be routed to the proper service using path-based routing, which works remarkably like an application load balancer, which you can also use with EKS. So when you decide to basically run this on AWS, your ingress controller option is actually an application load balancer, and it mixes up with Envoy and you can use either an application load balancer, or you can use Envoy, which is a CNCF project that for sidecar proxying, or you can use nginx actually. So you have a bunch of ingress control options. You can set up F5 for this. You can set up anything that will actually meet the Kubernetes CNI pod specifications. The CNI and pod specifications, you can run pretty much any network object that will support Kubernetes. So this is what you want to do when you actually want to set up pathing for different services, right? On a particular singular domain name, as an example. This is what an ingress controller or an ingress object is for. So it's slightly different from a service object, right? And that a service object is pretty much just IP to port kind of pathing, if you will. Whereas an ingress object can actually read the payload and redirect it based on rules. It does require a load balancer object, like a pod, to function. Here's an example. So on EKS, when you set the ingress controller type to ALB, what happens is that you're pathing and you might redirect to a certain node port, right, inside the system that's going to lead to a certain number of pods, or another one if the path is like web app 2. Like this could be mobile and desktop. This could be, Americas versus EU or APAC, right? You could redirect toward different pods if you needed it to. So when the request is made here, it actually goes to the ALB. The ALB is actually going to read the pathing on it, pick the proper target group. Because remember, application load balancers in AWS have target groups for those different paths, which means they're targeting different, in this case, different hosts. Well, in this case, just so we're clear, I think it targets all of the hosts and just hits the path once the Kubernetes gets a hold of it, right? And so it's going to hit either port 32,003 if it's one path, or it's going to hit port 32,004 if it's the other path. And the pod's then just going to handle the request, whichever pod it hits, right? Note again that the IP table rules in kubeproxy have been updated for all the nodes, so that if it hits 32,003, it knows it needs to redirect to one of these VPC subnet IP addresses on the network. So in a way, this doesn't actually work much different than a load balancer service type, except there's pathing here instead of just a straight up IP and port setup. So to make sure that was clear, because I might have misstated that, so I want to make sure that I'm being super clear here. If you need a network load balancer or a classic load balancer, you're going to end up using a service type of load balancer. If you need an ALB because you need pathing, you're going to end up using the ingress controller, right? That's a different object type. It's not a service type. It's not a service object. It's an ingress object. So let me show you this. So notice this doesn't say service as its kind. It says ingress. And then here are the different annotations. For example, for my application, the namespace it runs in, Notice the annotation is for an ALB, the subnet it's targeting. In addition, here are all the backend paths that it's looking at. Nginx service port 32003, right? And so these do actually hook into services, right? Notice the service name is web app and the service name is Nginx. So ingresses do chain into services. Good. I was just pausing for questions. All right. So moving past cluster IP, which by the way, cluster IP is internal or external? Which one is it?
Internal.
Internal only, right? Moving past cluster IP, moving past node port. Node port is internal or external?
External.
External. Good. Then we got load balancer, which we know is external, right? Because I can host out. Now then we got ingress controllers, which chain into the services objects we just talked about. Now we're talking about external names. Now, external name, all that is just a redirect towards like a CNAME, a DNS name. That's it. So, for example, if you set up an external name, what happens is the IP table rules say, hey, look, if you hit this particular port, I want you to actually go just redirect it to this name. In this case, it's like the relational database service on the lower right-hand side. That's it. This, by the way, is very useful, not just externally, but also internally. If someone you have a service and you want your internal web service to actually go to an RDS database, this is very useful, right? Here, by the way, is the service definition, right? Notice the kind is still a service, the type is an external name, and the external name is just the CNAME. That's it. You've got some namespace definition, of course, the name of the service in question, right? That's it. A lot more simple compared to the other things that we just talked about, right? It does leverage cluster IP, by the way, to pull this off. It just redirects instead to a CNAME instead of an IP address. Okay, little knowledge check. Which of these services can be accessed outside the cluster?
This is D.
D, right? So node port and load balancer can be accessed outside the cluster. Cluster IP is internal only, right? Good. What is a CNI? Is it represent a virtual network card, which is what A is? Is it a method for enabling instances in a private subnet to connect to the internet, which is what B is? Is it a K8s object that exposes an application running on a set of pods, which is what C is? Or is it a plugin that allows Kubernetes to have the same IP address inside the pod as they do on the network? Well, CSI, CNI, CRI, those are all container something interfaces, right? Like container networking interfaces, container storage interfaces, container runtime interfaces, right? And so those are basically typically just pieces of software. They're plugins that you can run inside of Kubernetes that allows awareness of the IP range space, right? So in this case, the answer is actually D, right? The container network interface. So note that we also have CSIs, which are plugins for storage. We have runtime interfaces, which are basically plugins for container runtimes. Container D and Creo, which we talked about at the beginning, right? So the CNI is just the network version. Good. Any questions thus far? Okay. All right. Let's talk about managing your IP space next. So I've talked about this several times, but one thing you just want to be keen about is making sure that you have plenty of IP addresses. Oops. No, go forward. Right. Note that up here, right? There were 65,000 IP addresses and there's 800 IP addresses attached to this. I'm sorry, 8,000 IP addresses attached to this system. That's pretty good because you can get 80 hosts, probably more like 70 actually, if you take away a couple IP addresses, but like you can get a pretty decent amount of hosts actually in an 8,000 kind of setup. And so that's actually pretty great. I might even try and go larger if I could, right? Because that only represents, 16,000 between these two subnets of the total 65,000 available IP addresses, right? So one thing to be aware of is that since it does allocate to each pod, you need to make sure that you have considerable IP space, depending on how large you think we're going to go. This is another reason, by the way, which I'm a fan of cluster it as a service instead of namespace as a service, because I can just put another cluster in another subnet and then just make sure there's transit gateway route rules between the VPCs, right? I can peer VPCs together if I want to go that route. Transit gateway is probably a better option. But so I have options if I want to hook VPCs together. So I'm very keen on creating clusters as a service instead of running into the limits of stacking too many clients, if you will, on the same systems. Now, if you're out of IP space in a cluster, you can add additional subnets by using what they call the secondary CIDR ranges. Just to say this is that if you want to include them, by the way, with EKS, they have to be tagged actually with kubernetes.io/cluster and then the cluster name. So, just know that there are actual documents that will allow you to walk you through the process of adding additional subnets to a cluster. So in this particular case, right, they added another subnet, in this case, I think a 32, right, to use inside the cluster, inside this VPC, and so they added another subnet. That's probably a more complicated topic than this single slide kind of denotes, in the sense of is that there's a few tagging things you need to do in order to make Kubernetes aware of them. So notice that additional subnets have just been added to the cluster. Notice that these are all in the same range, because if you run out of IP addresses in that particular 192 range, you can actually add additional CIDR blocks to your VPC. Just one thing to note is that while you can add additional ranges and then add the subnets to your cluster, there's in the VPC user guide, you want to read the document that says how to add a secondary IPv4 CIDR block to your VPC, right? So preferably you can avoid this either by running cluster as a service or just starting with the /16 and giving /18s or 19s as your sizes, right, for your cluster sets. So I have to say that 8,000 IP addresses is pretty sizable for a cluster. I might look at initiating a different cluster or do some other variation instead. Okay, let's do a little activities, and then I think we're moving on at this point. So how does traffic flow? So pod to pod on the same node. Let me ask you this. If it's pod to pod on the same node, how does traffic flow? What does it flow through? Does it hit the host network card? Does it use some kind of virtual network card? How do pods talk to each other if they're on the same node?
Is it going to just hit loopback to the cluster IP?
Well, if it's containers in the same pod, they'll hit loopback, right?
That's right.
But it actually is going to hit a virtual Ethernet device to kind of tunnel them together. So it actually won't even touch the host's networking loopback. It's actually just going to run through their own virtual stacks, if they will, right? Because there's virtual networking devices here, and they're just going to talk directly to each other because they're pretending to kind of, in a sense, run their own network on the host. So they're just going to talk directly to each other. That's pod to pod on the same node. Well, then, yeah. So then that begs the question: what if it's pod to pod on different nodes? How is that going to work? Are they going to talk through their own little private virtual interfaces? Are they going to use the host cards to talk to each other? Which of those two options are they going to follow then?
Host card. at both.
That's right. Mainly because the CNI plugin has basically assigned every single pod an IP address. So if you just want to talk to another pod on another host, you just say, I want to talk to that pod, and it will route out through the host's networking stack, talk to the other host networking stack, and get straight into the actual IP address of the pod because it treats them like virtual machines, right? And then if you want to go from external traffic to a pod of a particular service. So for example, let's say that you want to go straight into a host and go directly to a pod, right? You're not interested in a virtual IP address. What are you going to hit? What kind of service type? Is it going to be external DNS? Is it going to be a load balancer? Is it going to be a node port, or is it going to be a cluster IP address? If you just want to hit a node and go straight to a pod.
You can use a load balancer.
Sorry, Ram, I didn't hear that. Could you say that again?
I was saying you can use a load balancer.
So you can do a load balancer, but that's not going directly to the node. That's going to a load balancer and then going to a node, right? What if you just want to go directly to a node? You don't want to use a load balancer. So you know that one's off, right? Cluster IP, node port, or external DNS?
Do node port.
Node port, exactly right. Because remember, cluster, as you kind of know, cluster IP is not externally available. So this is external traffic. So you got to go to node port, right? And so in this particular case, external traffic is hitting the network card, hitting that particular port. Let's say it's 32,001, and then going straight to the pod, right? That's it. So really straightforward. What if I wanted, just to say this, what if I wanted to hit an external DNS service? What would I use for that? Cluster IP, node port, load balancer, or external? Let's go all the way back to this. I would hit external name, right? External name would then redirect me to DNS, right? So remember, cluster IP binds a virtual IP address that allows you to then talk to all of the pods in question. Node port binds a particular port on all the hosts, which then talks to a cluster IP, which then allows you to talk to all the pods, right? And then load balancer actually registers all of the hosts in the entire worker node set in the load balancer, hits a particular port, which then hits a cluster IP, which then hits the pods, right? And then the external DNS name actually just redirects to external DNS for a service. Okay. Talking about managing your IP space. All right, knowledge traffic. If you run out of IP space in your cluster, what are the two things that you can do to add more IPs to your cluster?
A and B.
A and B? Anybody else? Yeah, it is actually A and B, right? It's not C. You're not going to add more Kubernetes services. That's not going to help either way. You're not going to have pods on the same node share IP addresses. That's not even possible, actually. And you're not going to remove containers from your pods because that's actually not going to reduce your number of IP addresses. You have to remove pods, right? So you could reduce replicas if that was an option, but it's not an option here. Either add another subnet to your cluster if the VPC has capacity, or add a new set of IP ranges to your VPC, which then will allow you to add subnets, right? So there's a couple options there. Okay. So let's do this because it's 11:13. I said I'm going to run through the rest of this, and then we'll probably go to lunch, come back, and end up doing the lab. right? That'll be our day, it's like our morning at least, right? So I'm going to run through the service mesh pieces, and then we'll probably actually take lunch just a little bit early, and so maybe it'll be at 12 instead of like 1 o'clock, and then we'll actually run through the lab, and I'll make sure the provisions again, so just make sure that we won't expire, right? Okay. Any questions about those service objects or the ingress object? Good. Does anyone need a short break, by the way? Does anyone need like a bio break or anything? I'm feeling like maybe we need a break, like even if it was just 10 minutes. Would it be okay if we took a short break? Yeah. Why don't we take a short break? It's 10:15. Why don't we take 10 minutes just to be like time conscious, because we're gonna have lunch here shortly, right? And so it's 10:15 right now. Come back at 11:15. Come back at 11:25. So in 10 minutes, let's take a 10-minute break and we'll be right back. Okay. See you in a bit. I have to say, it's kind of funny in this kind of like COVID teaching, because now that I'm home, I have a 13-year-old and I get randomly attacked like a cat. He just like attacks me, like, because I grew up as a single child. So they just, him and his brother, like, just attack me at random. So I had an interesting break actually, where it was like, hi, let's test our strength against dad. So tons of fun. All right. All teenage strength trials aside, let's talk about service mesh. But before we do, does anyone have any questions about any of the networking stuff we just talked about? No? Okay, good. Then let's talk about service mesh. Okay, so service mesh is interesting because service mesh is what you do when you want to, like, to say this is like some of the challenges we have is like being able to dynamically configure how services are connected, how we can like get visibility in services and how to secure them, like TLS, SSL, right? And then kind of controlling how the network, like the packets are routed through your network. Those can all be interesting challenges with like microservices and containers, right? So, we have to be mindful of this because we've added complexity, and at the same time we want to increase control in some cases, like visibility, securing, that kind of thing. So to solve some of these challenges, right, like for service communication and securing secure service communication and like redirecting service communication, this concept of service mesh is been thrown out to like do things at scale. And basically what a service mesh is it is a dedicated infrastructure layer in which you can abstract away service to service communication. And it's done with a like connection of lightweight proxies. So if you can look at the screen here, like the purple piece is like a proxy between the service and any communication that goes to the service, right? And why would you use this? Well, for example, if you don't want your developers having to worry about rate limiting or doing SSL or TLS, for example, in front of their application, like encrypting traffic, you can actually just abstract that away and configure that intelligently through a service mesh so that the developers can just focus on writing features for their code, publish those features, and you can make sure that compliance is achieved by setting up a service mesh that then enforces things like rate limiting or TLS SSL. Like it actually does it on behalf of the developer who is now, just writing their container service and the pod is encapsulating out, right? There's also, you can write like business logic rules to say, go here, do this, right? Go here for the database, that kind of thing, which of course you can do in other ways as well. But a service mesh is going to monitor all of the inter-service traffic and allow you to configure the traffic flow on the wire, right? So the mesh, by the way, tracks all the data on the wire, which of course you can also use. So how do you know whether you should add a service mesh to your cluster, right? Well, again, if you need things like rate limiting, circuit breaking, you know, you're like, hey, I've got 5 applications that actually need to use SSL, and we have other feature priorities, then you might actually put a service mesh in place to actually attend to that. If you have enough that like need that, or maybe like someone's come in and said, look, none of your applications are secure, are using TLS, and so I need you to enable TLS across your entire like 30 set of applications. Turn on service mesh, there you go. Now, popular service meshes are Istio, Linkerd, or Linkerd as some people say it. And then also AWS has one called AppMesh, right? AppMesh is AWS's proprietary kind of Istio, if you will. But they all work kind of in similar fashion. Now, AppMesh is their kind of recommended, like their like native tool, right? It automates, by the way, and abstracts the communications of infrastructure, right, through your services. And so AppMesh provides like this service mesh functionality in like a managed service, basically, right? So you can get like consistent communication, you can get observability, you can get failure isolation, right, to handle failure isolation and protection even more than what a load balancer can do. And then you can route, like you can control the routing inside your infrastructure a little more granularly. So the AppMesh API can basically route to any of the primitives that you have in AWS. And this includes containers on ECS or EKS using either the Fargate or the EC2 launch type. It also can, AppMesh can actually point or hook into containers on EC2. So if you're running like Kubernetes containers on EC2, or if you're just running applications on EC2 and you want a service mesh on top of them, you don't even actually need containers. You can actually just be on a virtual machine if you want to run a service mesh. So the way this works is that Envoy, which is a CNCF project, runs in a sidecar pattern. Actually, is that right? Sidecar pattern? Or is it more like an ambassador pattern? Anyway, I'll come back to that. Anyway, it basically runs as a sidecar container inside of the system. And so the proxy, the Envoy proxy, basically just acts as a like ambassador, like on behalf, a proxy on behalf of any and all traffic that hits, that's going towards the microservice, right? And so, you know, this container, by the way, is going to configure your pods to use the AppMesh traffic rules for the virtual nodes or the virtual routers or the virtual Ethernet devices that we saw earlier. So the reason that you're going to use sorry, was there a question? So the reason that you would use an Envoy sidecar proxy instead of just adding more libraries or application code is that, one, this is going to take work off the developers. It's going to ensure the security, visibility, and other circuit breaking and rate limiting functions are actually, you know, just handed by like the application team, like maybe even the infrastructure team in that particular case. It supports any application language, so it doesn't matter what the backend application language is for the container because it's a separate entity. And it really simplifies visibility, troubleshooting, and deployments once you have it set up. So all the pods, when you have an AppMesh or even Istio or whatever, are given a proxy. So all traffic that's bound for your pod, instead of flowing directly to the pod, now goes to the proxy. The proxy in turn is going to talk to the microservice inside of your pod. So you can actually basically add the AppMesh into your pod specification just by using like the AppMesh sidecar injector. So the injector, by the way, is going to install a webhook and then inject the sidecar container image into Kubernetes pod. So you can actually do this live. You can actually inject it into the system if you want to, in specific labeled namespaces. Now, not everybody needs a service mesh, so I just want to be upfront about that. There are tremendous benefits of using a service mesh, whether it's AppMesh or Istio or Linkerd. There's tremendous benefits. They all use Envoy, by the way, as the proxy, underlying proxy component. So all those technologies I just mentioned all use Envoy, which is what we're looking at here. But just like be careful, because if you don't need this, then you're injecting unneeded complexity into your cluster. If you don't need rate limiting, caching, you're not running into a TLS problem, you don't need more observability. There are great things that this can do, but it can add complexity to your system. So just make sure there's a business need here for this, or a non-functional requirement need that this is going to solve, right? Here, by the way, let me move this out of the way. Here's some custom resources. So the mesh, by the way, in addition to the sidecar proxy, the mesh actually is going to add the like other additional components, right? It's going to have a logical pointer to a discoverable Kubernetes service. That's called a virtual node. That's the gray box on the right-hand side. A virtual router is basically going to handle traffic from one or more of the virtual services that are inside your mesh. There's usually a route associated with a router, right? And then the service itself is an abstraction of an actual service that's provided by the node. So, for example, each virtual service has at least one virtual node. And so the proxy is going to talk to the virtual service, then go through the router, and then hit a virtual node. So, and remember, by default, Kubernetes only has like a set of only core objects. So in order to get these other objects inside your Kubernetes cluster, AppMesh or Istio or Linkerd are actually going to create new custom resource definitions for these custom objects. So you're not going to have virtual nodes, you're not going to have virtual routers, you're going to have virtual services that all like point to the proxy, right? So there's more additional components. If you're sitting here going, Michael, this sounds even more complex than the stuff that we were just talking about, it is. So I want to be very cautious and clear, right? Service meshes are wonderful things, but if you haven't like really gotten Kubernetes down, don't go to service mesh just yet. Make sure you're comfortable with Kubernetes, then get into service mesh. Troubleshooting a service mesh when service mesh goes awry, by the way, is like a really bad game of Clue, that old board game from like the 70s or 60s. Just be aware, okay? Now, all the AppMesh stuff, by the way, is available on an AppMesh. There's an AppMesh controller, if you will, that actually gets started into the cluster. The AppMesh controller, by the way, is actually on a GitHub repo. So if you type in the AppMesh controller for Kubernetes, you'll actually find it out on GitHub. So here's the summary of the module, right? Is that Amazon EKS does use the CNI to enable pods on different nodes to communicate. Kubernetes services use the kube proxy to route traffic to pods within the same application. Make sure that you have enough IP space for your cluster. Remember, every single pod is going to get an IP address off of this like range that you set for your VPC. So make sure that you've got plenty of IP addresses for your projected number of pods that you're running in your cluster. Service meshes are a great way to secure, observe, and control communications between your services if you actually need a service mesh. The cost of this increased and abstracted security and visibility and rate limiting and caching and all this network control is complexity. Make sure that you're ready for that complexity before you throw this in production. Make sure you've got your EKS and Kubernetes stuff down before you throw service mesh in production. Because one of the some of the worst deployments I've ever seen is where you've got a green team, for example, moving straight into Kubernetes. They've thrown a service mesh on top of it, all this other stuff, and it's like, and they're not ready because they don't have experience troubleshooting Kubernetes, much less the complexity of a service mesh. Remember, you've got an AWS option with AppMesh, you've got Istio, and you've got Linkerd has your options for service meshes. They all use Envoy as the underlying proxy. Any questions about any of this? Okay. So my intention here is that because we have about 35 minutes left, which is not long enough for us to do the lab, I'm actually going to pivot on to the next section because I want to make sure that I'm honoring your time. And then when we come back from lunch, we're going to roll right into lab 5. Like that's going to be our main focus or thrust. So anybody have any questions about anything that we just talked about? Because that was a very heady and complex section that we just covered. Was there anybody, by the way, who just now, like I went through all that and you're like, Michael, I already knew all that. I already knew everything about the networking pieces already. Just curious. Okay, good. Well, then definitely hopefully you all learned something new. I know there were some like subtle reminders here from me as well. Okay, so we'll come back to lab 5. I'm gonna sit on that for just a second. Let's see, just to make sure we're good. Yep. Cool. So the next thing we're going to talk about is actually authorization and authentication inside of, inside of AWS. That was networking. Where's the one that I just started? There we go. Cool. Okay. So this, by the way, is going to talk mainly about RBAC, and some of these pieces we've already touched on, right? Because we saw earlier how when we run kubectl, it actually hits Kubernetes. Kubernetes talks through the IAM authenticator to actually talk to IAM, gets an authorizer, an authentication response back and says, hey, you are this person. And then it uses a role-based access control to map that IAM role or user against what it knows should be possible against its own basically role-based access control database, right? We saw that earlier. So we're going to try and understand a little bit about the AWS shared responsibility model. We're going to talk about auth and authentication, authorization, authentication. Talk about IRM and RBAC. I might skip the demo and show you later, just to make sure we're not oversaturating you. It just depends on our time. And then how to manage pod permissions using RBAC service accounts. Now, in AWS, hold on, let me just make sure this is going. Oh yeah, in AWS, just so you know, you are responsible for the things that you put in the cloud and the things that you configure in the cloud. But if you can't log into it, you can't see it, you can't configure it. If it's any of those 3 levels, you're not responsible for it. So if you can't actually log into the operating system, like for Fargate, for example, guess what? You're not responsible for patching the underlying operating system for Fargate because you're not actually able to log into Fargate. You can't even touch it. So you're not responsible for it. So AWS takes care of everything that AWS controls, and you take care of the things that you control. So that way there's this simple kind of line that says, look, if you can configure the firewall, then you're responsible for any configuration from a security perspective. But you can't log into the firewall and patch it, so you're not responsible for patching or defending the firewall from that perspective. And so in this model, the blue is customer responsibility, security in the cloud, not security of the cloud. Amazon takes care of all the stuff in orange. But if you put data in, you're responsible for the security of that data, not necessarily from the container perspective, but how you can configure the availability of that data. So the line here is, again, if you can configure it, control it, log into it, usually that order of things, then you're responsible for security of it. If you can't, it's all AWS. This is why, by the way, when we launch our Kubernetes clusters, we put them on private subnets and we put load balancers on the public subnet and expose those to the internet. Why? Because Amazon's responsible for defending those objects, those load balancers, because we can't log into the load balancers. We can just configure some of them. And then since our Kubernetes clusters are on private subnets, nobody can get to them from the internet unless they somehow break the application load balancer, right? So here is an EKS specific shared responsibility model with managed node groups. And look at this. So what you notice here is that with managed node groups, right, you're not responsible anymore for the OS, the kubelet, or the AMI configuration. Amazon provides that for you. So Amazon, AWS in particular, is responsible for building the patched versions of the EKS optimized AMI, like that boot image, right? For those managed nodes, when bugs or issues are reported, that's all going to be Amazon. That's not you, right? Now you're responsible for deploying the patched AMIs, but you're not responsible for creating them. With Fargate, you're not only not responsible for the operating system, you're not responsible for worker node scaling either. They'll take care of that for you. You won't even see that. But RBAC, the cluster configuration, the VPC configuration, if applicable, right? Your container application images, right? Your customer data, all that's still you. You know, we still got the blue stuff, right? We still have to manage and protect our applications and data. Questions on that? Okay. All right, so we're back to this. Who is the person? Are they like, who are they? Are they who they say they are? And do they have permissions? What can they do, right? So again, depending on the API you're using, you're either authenticating against IAM, which by the way, in all cases, you're authenticating against IAM, right? But authorization, if you're using an AWS API like EKS ETL, you actually have to use the AWS IAM API, right, to authorize. But if it's Kubernetes, Kubernetes will determine what your permissions are. Because remember, Kubernetes doesn't maintain a user database, so it needs IAM or Active Directory or something else to say, who are you, prove who you say you are. But to grant permissions, Kubernetes will handle that itself. It'll be like, hey, here's the role associated with you, right? For example, scaling a particular node group, right? You want to go to 5 nodes from like 3 or 4, for example, right? This is going to happen. It's going to require not only the AWS API, but it will actually require the authenticator, like the authorization of Kubernetes as well, right? So creating an EC2 instance, guess what? That's pure Amazon. That's pure AWS. You're going to authenticate against IAM for that. Now, adding the nodes to the cluster requires the system of Kubernetes to be aware that these nodes are now its like nodes to use, right? And so that's going to require authentication against IAM. And then authorization is going to come from the actual Kubernetes system itself. Is that clear to everybody? So remember, IAM works off of users, groups, and roles. And federated users, by the way, you usually use roles to get access into AWS. And each of these particular entities, these core entities under who, get policies that give them their permissions. And so you can actually come in and set your IAM policies because they control access to resources. Now, with Kubernetes, the constructs in the role-based access control are very similar to the things that you see as far as like who can do what, right? Who's attached to the policy. And the policy says, this is what you can do. These are the actions you can perform against these resources if these conditions are met, right? Same thing here. Kubernetes says, okay, what is the subject, right? Because remember that we're talking about certificate subject lines, right? Because there's like subjects, right? What are the subjects? Like who is this person coming in, right? And then what can they do, right? So resources, like what resources are the objects they can actually touch inside the cluster? And then what are the various verbs that they can execute against the objects? This is no different than how AWS says, hey, what services and what can they do against these services? Now, a role or a cluster role is different because a role usually is specific to a namespace. So it's a role, by the way, sets basically actions against a particular namespace. A cluster role is a cluster scoped resource. So, for example, creating namespaces is a cluster-wide thing. Creating a pod in a particular namespace is a role-based thing. So roles are for resources that are namespace, and cluster roles are for objects that are not not namespace. Does anyone remember the command that you would run in order to find out which resources are namespaced and which ones are not? Does anyone remember? I know I'm asking like heady questions on this really slow morning. Hold on one second. Oh man. Sorry. All right, good. All right, instances stopped, sessions expired. Sorry, I don't get to show this as quickly as I want. Does anyone remember the command that you can run to actually show whether an object has a namespace capability or not? I can actually just type it in the chat instead of everyone waiting on that. So it's kubectl API resources, right? So that came up. See how quickly that came up? So amazing. Terminal was disconnected. I need you to reconnect that terminal. Here we go. So kubectl API-resources. This will list all of the objects that can be namespaced or not namespaced. So be aware, right, that not everything here is namespaceable, but if it is namespaced, you can use a role to control access to it. If it's like component status or nodes, those are cluster-wide permissions. So cluster role is going to be what you need to look at for that. So again, who? Well, that comes from IAM, but that is actually defined as a subject inside of Kubernetes because the subject needs to match what comes from IAM, right? The what is the various objects inside Kubernetes, right? The resources. And then the verb is our actions that are against those resources. Can I get them? Can I list the entirety of them? Can I create them? Can I update them? Can I modify them? Sorry, can I delete them? Right? So role and cluster role are the distinctions here. And by the way, there's also a role binding and a cluster role binding, and that will grant the permissions, right? So when you bind the operation to the resource access to the subject to the role, that's called a role binding or a cluster role binding. Right? So when you can see it down here. Resources and operations are bound to subjects. And that actually allows Kubernetes to know what a particular group or user can do once it's authorized. Once it's authenticated. For example, here's an RBAC role. Look at the kind that says role up here. Here's the metadata. Here are the rules, right? So this basically shows a role that grants access to certain operations on this particular pod. The null basically entry for API groups indicates like it's the core API group, right? So the resource is pod. The verbs are get, list, and create. Here, what's happening is that we're using a role binding. So notice the kind has changed. It's no longer a role, it's a role binding. And what it's doing is it's the subjects, by the way, are the kind or user. The name is student. So if someone can authenticate as the student against Kubernetes in IAM, then it will basically grant access to the RBAC authorization API for that subject. And this grants the pod creator role, right, to this user, a pod creator role. So this isn't necessarily this is the pod creator role, right? And notice here that we are binding that role to that user, to that subject, right? It's the subject, really. The name field in role bindings is actually case sensitive. Yeah. Okay. Here's a cluster role, by the way. Notice the kind here. It's cluster role. It's called the secret reader. Notice that if it's blank in between the quotes for the API groups, it actually gets access to the core set of APIs. Resources are secrets, so it can actually access the secrets objects. It can get, watch, or list objects. You can, by the way, specify specific secrets if you want to. Notice that no namespace is specified in cluster role. So notice that here the namespace was default in the role. Here in the cluster role, there's no namespace in the metadata. Why? Because cluster roles are not tied to namespaces. They are across the entire cluster. So when you're binding a user to an RBAC cluster role with a role binding, right? Just to kind of like clarify this, here, by the way, notice the kind is a role binding. Name is read secrets. Kind is user for subjects, and the name is student. And then the role reference is cluster role. So it's referring to a cluster role and a secret reader. So notice that the only difference between a cluster role binding and a cluster role binding, right, is like the fact that we're referring to a cluster role. So you can't actually bind a cluster role with a role binding, but do note that I believe that this user will actually be limited to the namespace development because it's got development listed as a namespace. So you can actually not use necessarily a cluster role binding, but use a role binding to bind to a particular role, some cluster permissions, but they will be limited if you need to like specify a namespace for that like cluster role, if you will. So note that for objects that require a cluster role to access, you can actually bind those cluster roles like to a role, right, to a particular namespace to limit their access. So you can actually use a role binding to bind a cluster role instead of using a cluster binding to bind a cluster role. In this particular case, we're using a cluster role binding, not a role binding, to bind basically this group of admins to this cluster role of secret reader. Notice that there is no namespace limitation here, so they will be able to read secrets across the entire cluster in any namespace. Any questions about any of that? Roles and role bindings, cluster roles and cluster role bindings. Remember that with a role binding, you can actually bind a cluster role, right, to a subject. But that will namespace it so that that will limit the cluster permissions to the namespace that you specify. Okay. All right, what are the list of allowable actions and resources? Okay, so with IAM policy, for example, what is that? What do you typically link an IAM policy? Like, how does that like equivocate inside of Kubernetes RBAC? For example, what's the equivalent between an IAM policy and what inside of Kubernetes? So for example, a role or a cluster role, right? This is what would be equivalent to like an IAM policy, right? Which basically defines permissions, right? And again, that one's hard, so I can get it, right? So if you want a list of allowable actions and resources, you need to look at the IAM policy, and then you need to look at the role if you want to see that inside of Kubernetes. All right, so we're getting warmed up here. Which of these entities is going to grant a set of permissions to an identity? both on the IAM side and on the Kubernetes side. So if you want an identity to assume a set of permissions, right, you can actually grant a role. And if you want to do that inside of Kubernetes, that means you have to grant access to resources and operations to a subject. That act of granting is called a role binding, right? Okay, so then here's a question. What does Kubernetes call, like what's the equivalent of an IAM user over on the Kubernetes side? What's the equivalent of an IAM user here?
Like subject.
Subject, right? That's it. That's not one of the official questions, but the subject is it. Good. Good, good, good. All right. Just checking our time. We're good. Okay. So we're going to go through this last section and then we're going to stop. When you come back, we're going to pick it up with Lab 5 and then we're going to come back to RBAC. And I might do a little bit of a refresher here just to make sure that everyone's keeping pace. Okay. Now, when we map between an IAM role, which is a set of an identity, like a disguise, if you will, an assumed set of permissions, to an RBAC group, right? So, for example, if a role here has authenticated with a Kubernetes API server, RBAC is going to control how much permissions the role has to run Kubernetes commands. So mapping an IAM role to an RBAC group grants the role permissions defined by the RBAC group role, like to what it can do in case. Now, in this particular case, there's a config map called AWS auth. Where's the name? Oh, there it is. Okay. So here is AWS auth. This config map is what creates that relationship. It basically maps the IAM name here. Notice it's pretty long, actually. To these particular groups, like system nodes or system bootstrappers, right? So when IAM authenticates the identity, the API server is going to read the config map in the kube system namespace right here, right? To figure out if the RBAC group is associated with the user in question. So this particular role, ARN, is reconciled to make sure it matches what's submitted. If it is, the user gets these permissions. That's it. Here, by the way, is the config map again, edited to add additional roles. Ah, yeah, there's another group here. Good. So this particular group has web admins in it for this particular web admin role that someone can assume, right? Notice the username is defined as web admin. What can this particular system do? It can authenticate, gain access to the cluster, and basically perform actions that the RBAC group web admins permits them to do. So notice this is a system group that this is allowed to do. This is a group inside the RBAC controller for Kubernetes that is what this can do. All right, let's take a look at this little demo here. Create a new role in Kubernetes RBAC for your web administrators. So here we're going to look at the role configs, webadmin.role.yaml. I'm not even sure where that file is actually. Huh, interesting. Anyway, we'll do this at least verbally. So notice ignoring the API version, the kind is a role. Here's the metadata. Notice the namespace is web, right? Which only exists in role. It doesn't exist in a cluster role, right? Notice here that we're defining the API groups, the resources, and the verbs. Here, the API group basically is any, right? This role grants anyone broad permissions in the web namespace, but no permissions outside of the web namespace. So any API group, any resource, any action, this is truly an admin of the web namespace on the system. You would apply this, and then what it would do is that it would basically create, it would create this role as an object, and it would just say a little line that says, role web admins is role created. That's all it would say, right? And then here, what's happening is that we're now on to a role binding. Again, in the namespace web, and here's the name of the web admins binding. And then it's referring to some just basic authorization API groups for the role in this particular web admins role. So it's basically, granting the permissions necessary for it to do authorization. And then what it's going to do is it's basically going to associate, right? The web admins group, right, with this web admins role. So here's the role reference, and here's the subjects in question. So a binding ties the role to the subject. So any identities, by the way, that are mapped to this group get these permissions. So then we come in and we edit our existing AWS-auth config map. So this is something really to remember, is that AWS-auth config map is something you have to edit it in order to enable access from an IAM user into your Kubernetes cluster. So here they've edited the config map, and then here we're going to show it basically. And what they've done is web admins, that particular web role arm listed here down in this area, is now associated with the web admins group, right? I'm so surprised to see kind at the bottom, by the way. Usually it's up at the top. That threw me off a little bit. And notice this username, web admin, right, is now associated with this group as well. Okay, so here's a little knowledge check over what we just re-verified. What makes it possible to use IAM credentials to authenticate to a Kubernetes cluster? Which of these actually makes this work? What is the service or plugin that makes this functional? Is it a native feature of K8s? Is it an RBAC service accounts? Is it the OpenIDC Connect provider, or is it the IAM authenticator for Kubernetes? Jarvis, I saw your answer. Anybody else want to throw their hat in the ring? D is the right answer, right? Going back to our original map, right, of kubectl, Kubernetes, IAM authenticator, coming back to Kubernetes, then looking at the RBAC setup, and then granting kubectl permissions. Yeah, that's it. Good. Now, remember that there is a cluster admin RBAC role. So when you create the cluster, by the way, there is automatically a cluster admin RBAC role. This is similar to the root user in a Unix Linux system, but it basically grants full permissions with no restrictions. So, and then Kubernetes is going to create an RBAC group called System Masters, and it's going to bind the cluster admin role to that RBAC group called System:\Masters. So in order to maintain the security of the cluster, you've got to manage access to that systems manager RBAC group really carefully, right? So, if you do an RBAC lookup against just groups, for example, it will list out the group on the left-hand side and the role that is bound to that group on the right. And so notice that cluster admin, the role is actually bound to the group systems masters, right? So Kubernetes has a default listing of all the default roles and role bindings inside the system. So the RBAC lookup, by the way, is a plugin for kubectl that allows you to kind of like search for roles. This is not a default behavior of Kubernetes, at least not that I've seen. This is definitely a plugin. Let me pull this up, by the way. Let's see. I don't think the plugin is installed by default. Yeah, there's a plugin. It's done by a company called Fairwinds, which, by the way, Fairwinds is a great, awesome company if you haven't heard of them. But Fairwinds Ops has an RBAC lookup tool. It's out on GitHub. No, that's good. RBAC lookup, here it is. Fairwinds, by the way, is a strong contributor to this space, so I'm actually going to post this in chat. This is a great way. By the way, you should save, if you're doing Kubernetes, you should get to know Fairwinds, and you should actually save this general like repository on GitHub. They have a bunch of really like cool tools out there. Some of it does require some checking, but like Polaris is the open source version of their product that basically validates best practices against your cluster. Really great tool. Highly recommend that you look at this company. I have no affiliation with them in any way, shape, or form. I have no affiliation with anybody. I do not own stock, but I think they're privately held anyway. But like, this is a good company to stay connected with. They are strong contributors to the community, and will teach you a lot about Kubernetes if you want to know more. So managing cluster admin and managing these particular like system master groups is actually exceptionally important. Here, by the way, we're getting the cluster role admin and going wide on the YAML to basically say, look, I want to see. And if you look at these rules, look, it's got star.star everything, right? Non-resource verbs, resources, API groups. It has basically full control. So you can come in if you want and create dedicated roles for creating clusters, just kind of moving past the root user. You know, like you can do like create cluster role. You can do delete cluster, pass role on. These are all EKS conventions, by the way, right? And so just know that you can actually come in here and create, you know, to like check in and create a cluster creator, for example. So for example, this is a student who has like create cluster, describe cluster. So note that when someone does something inside the cluster, so like the IAM identity that you use to create the cluster is the identity that's mapped to systems masters. So let me say that again, just so you're paying attention. Is if you start a cluster with a certain ID, that is the identity that is mapped to systems masters. That's why, by the way, why some of you couldn't see your clusters inside of EKS is because for whatever reason, your user ID didn't get mapped inside the cluster from an IAM perspective so that you could actually see the cluster from the console. Without some of those permissions, you can't actually see the cluster in the console. You can't talk to it, right? Okay. Let's stop there since it's 12:13 before we get into managing permissions using an RBAC service account. Does anyone have any questions about the cluster admin or RBAC roles, RBAC role bindings, cluster roles, or cluster role bindings? Anyone have any questions about any of that? Okay. Just to say this is that what we're going to do for lunch is that we're actually going to come back and we're actually going to do exploring EKS communication. I'll make sure the labs are warmed up. And then we're going to give you a little break on RBAC. We're going to come back and finish RBAC just in terms of like service accounts and some of the other pieces. Then we're going to do security and do a secure lab. And then we're just going to talk about upgrades on EKS, right? So when you get back, we actually have about maybe 3 hours worth of material left, plus the pieces I'm going to cover on training and whatnot. So, it'll probably be about 4:30 or 5, depending on the questions and engagement, and we'll probably be finished. I'm totally fine staying until 5:30. I'm just kind of giving you a precursor of like where we're headed. Okay. Questions, concerns, curiosities? Okay. It's 12:15. So come back in an hour at 1:15. So 60 minutes if you're on another time zone. So we'll be back 15 minutes after the next hour, top of the next hour. So we'll see you in 60 minutes. Okay. Everyone have a good lunch, take a break, get some fresh air, get your brains fresh. We'll finish out our last portion of day 3. All right. We'll see you in a bit.
All right, thanks.
Man, a little gap there. Oh, well. So in this particular case, right, you need basically the identity and the policy for AWS, and you need permissions inside Kubernetes. So you're going to have a mapping to a group with the correct permissions. Now, this isn't using the OIDC provider that we were talking about earlier. This is just using the IAM authenticator, which we looked at before, right? So this is actually pretty much more simple because it's not a service account. It's just a user, right? And that's it. Now, this is the one, by the way, that we just finished, right? Which is that there's an application running that needs to collect data from pods, analyze the data, and store the results. So this one has 4 components. So you need the identity, you need a policy for the identity, and what other 2 options do you need outside of A and B in order to make this work? Anyone take a guess from me? Which of the 2 out of C, D, E, and F do you need to actually make it so a service account can actually talk to AWS?
So is E and F?
So a trust between the IAM role, the RBAC service account, and an OIDC provider is absolutely correct. That's 100%. Because without that 3-way trust, you actually can't get the service account for the application to actually function, right? But we've got an identity for IAM. We've got a policy for IAM, which gives us our permissions. And we have a trust, which gives us basically the ability to authorize and authenticate. But it's definitely not F, right? And the only reason is that that's actually only reserved for like absolute emergency use only. That is the root user. You do not give pods root access to the entire cluster, which is what that role does. So it's definitely not F, right? F is hardly ever used, but E is definitely on the mark. So if we have an identity in IAM, we have permissions in IAM, and then you chose E, so that's which is perfect, so that we have now a set of permissions, or at least a way to authenticate against IAM. What are we missing on the Kubernetes side for that application? Is it D or C? Because if we're going to run a pod has an identity, what do we need for that pod for that identity to work?
I'm not sure which one it would be out of C and D.
Well, if we're running an application, you will always need a service account.
Okay.
So just to make sure this mapping is super like in your mind, our minds, not just yours, right? But everybody who's listening, right? If you have a user, you're going to need an identity in IAM, right? Because remember, Kubernetes doesn't have identities. Oh, don't get me wrong. It has users, right? It has groups, it has service counts. And those are just mappings, though, when you're running an EKS, right? You have to map those back to an IAM user, typically. If it's an application, it must have a service account if you want it to have permissions. Not negotiable. If you want a pod to have access to AWS, it has to have a service account. Now, by default, it runs as a default service account. So in this particular case, the only thing that was missing is that it needed a service account. But the 3-way trust is the other piece that's like super important, right? The rest of this is all AWS specific. I need an AWS identity and I need an AWS set of permissions, right? The rest of this is all Kubernetes specific. Good. So we just ran through an entire module that was just about Kubernetes and IAM. including access to the AWS API. We talked about a variety of like ways of authenticating and whatnot. And that was the end of the module. I just want to do a quick check-in. At this point, is everybody doing okay? Because I'm a little worried about you all being overwhelmed with information, because I'm not getting responses from people, which is totally fine. It doesn't just to be clear, like in a public class with people who don't know each other, it's not necessarily common for people to speak up and talk. So I just am checking in, because sometimes that could be an indicator of just like, hey, we don't really know each other, so we're just not talking. Or it can be an indicator of like, oh my God, Michael, you've killed us with complexity. So I just want to check in before we move on to the lab. Is everyone doing okay?
I'm good. I mean, all of this, some of this is new, but a lot of it is not. So I don't really have any questions until I actually start deploying.
Okay. Thank you for that, Mike. Yeah, definitely want to know. Okay. Well, if everyone else is good, then let's pivot over to lab 5 and let's do some Kubernetes networking. Okay. Before, again, just a little thing, just like a reminder, is that a lot of this is actually on the EKS workshop. And you might be like, Michael, why do you keep talking about this thing? But like, just remember that if you need, actually, I'm going to switch over. If you need to practice this, for example, like under the beginner sections of the EKS workshop, this actually talks about how to use IAM groups to manage Kubernetes access. This talks about IAM roles for service accounts. So just remember that there are free public labs here that you can run on your account all day long to practice how all of this functions, including exposing services, stateful sets, running Fargate, but particularly for the RBAC stuff that we went over, it's here, right? There's also, if you go under the intermediate section, you can actually get into more advanced things like OPA, the Open Policy Agent, right? And let's see, how to create custom resource definitions, because we've talked about that, but also OPA again, which OPA is like the meta advanced thing that you do inside of Kubernetes to manage like policy-based controls, right? So just know that this is a really valuable unlisted public workshop that you can use and do, right? That can also round out some of these concepts. But we'll talk about that towards the end of the day as well. Okay, so let's talk about networking. So in this lab, because we're going to go back after doing RBAC, we're going to configure and deploy an app mesh, because we were talking about like app meshes as being like a service mesh, right? Like of which Istio is probably the most popular open source version, and how to create app mesh constructs such as virtual nodes, virtual services, and virtual routers. Remember, I said that service meshes can do amazing things for you at the cost of increased complexity. So you're going to deploy a simple application to like show how it simplifies application deployment, then implement a sidecar and a sidecar injector, and you're going to run a canary test to verify functionality. Remember, this is going to be slow and by the numbers. We do allocate an hour for this, and so it's currently pretty close to 2 o'clock. So you have pretty much close until 3 o'clock to run this. Actually, let me just verify that I'm accurate with my times, because I remember it. Yeah, it was a 60-minute lab, right? And so that's going to be what we're going to spend our time on. Now, if we go look at the lab itself, which, by the way, oh, look at that. Once again, one errored out. That is, now I'm a little squirrely. Don't do that. So here, all of your instructions are here, right? So bash and host, we're going to look at the DJ app. We're going to install the integration components, the virtual node services, etc., into Kubernetes, right? Then we're going to deploy the app mesh components, create virtual nodes and services, load the injector and actually like load it inside of a running application, and then do some canary testing with this kind of application release. And if you need additional resources, like you want to understand more about Envoy proxies or Kubernetes DNS, it's all here, right? That's going to be the next hour. So go ahead and hit Start Lab if you haven't already done so. And that should get you started. And then we're going to spend the next 60, 65 minutes. So I'll check back within an hour. Otherwise, go do your thing, and I'll be here in case you need assistance. Let's turn on some recording. Let's share a screen. Okay. This next section actually only has 4 modules to it, which is basically talking about how to secure cluster endpoint access, which by default is publicly accessible, but authenticated by IAM. So, right, probably crackable somewhere in the world, but not by most people. We're going to talk about how to improve the security of your security workflows, how to improve host and network security, how to manage secrets, and how to prepare for Lab 6. So let's talk about securing endpoint, like cluster endpoint access first. So how do we increase the security posture, basically, of our clusters? 2 ways, obviously, restricting the endpoint access itself, but also enabling control plane audit logs, so we can know what's going on. So you can increase basically the security of your endpoints by basically just managing the endpoint access. So the API endpoints of an EKS cluster are basically used by the worker nodes and tools such as kubectl to communicate with the control plane. They're public by default. This is not inherently unsecure because any connection to the control plane is encrypted. It requires authentication. Any connection to the API server also needs to authenticate with the user or service account. So it's not like it's just sitting wide out there, but it does open it to opportunity, right? Which is not ideal, especially if there's a bug somewhere in the system, which, Kubernetes has never had any bugs ever in its history. So it's not like it's an insecure system. I'm just kidding. There have been tons of bugs with Kubernetes. So it has happened. It's a relatively new piece of software, right? 2014, that's relatively new. So cluster endpoint access, by the way, if you click on manage networking, will allow you to not only limit it to, say, public or public and private or private only, but you can also edit the sources that can actually talk to the traffic. So just like a security group, you can come in here and actually limit who can talk to it from a source perspective, right? And when you're using a private only, by the way, API access, it would be useful to configure something like a Cloud9 or a Bastion host or some kind of other management server. Like if there's like configuration pipelines or whatever, or administrators running kubectl, that way they can just jump into the box and then run the workflows they want. So make sure that before you turn off any public availability, that you troubleshoot immediately. You don't want to figure this out at 4 o'clock in the morning, right? It's not going to be awesome. And then other than changing the firewall and the public and private access of your cluster endpoint to get to the data plane, right? Sorry, the control plane, not the data plane, control plane. You can also enable audit logging. Now, you saw me do this a couple of days ago where I actually just went in and I was like, you know what? I want the API server, I want the audits, I want authenticator, I want controller manager, I want scheduler list. Let me just check all these, right? You will incur costs for the logs that are stored in CloudWatch, but just weigh those costs against your security features, your security requirements or needs. And then outside of managing your endpoints and getting like visibility into what's going on with the data plane, the control plane, I keep saying that, the control plane, right? You can also improve the security of your workflows, right? By basically reducing in a sense, your attack footprint. So smaller container images are really good, making sure that you're have verifiable, at least scanned sources. Scanning for vulnerabilities is a huge part of this whole thing. And you want to do that continuously, right? Anytime a new container, either sourced externally or created internally, is made, it needs to go through a scanning process. Now, you do want to reduce the attack surface of containers because this is really the first line of defense against an event. A non-secure poorly constructed like container image will allow a third party to escape the bounds of the container, and it will gain access to the host, right? So you want to reduce the attack surface on your container images. So for example, removing binaries, use multi-stage builds where you're sourcing from another container and then dropping it as you build the next container. So that way the tools that were used for build are not there. Inspect the image, for curated images, like use something like Dive or Claire. Dive, by the way, which is who does that? W.A. Goodman. Hold on one second. We gotta deviate for just a second. Dive is a tool that allows you to peel back container images. GitHub.com. W.A. Goodman. Is that the guy's name? Is it Dive? Hold on. Let's see if my brain is working. Aha, here it is. W.A. Goodman Dive. So like this is a great little tool, for example, for exploring Docker image and layer contents. You definitely want to grab this URL, which it'll help you discover ways to shrink your Docker/OCI image, right? So this is a cool little tool. So you just dive your image, right? And what will happen? You can just straight into analyzing it. So great little tool to have. Ooh, excuse me. Sorry about that. Let's see. Build images using Scratch. So don't source for anybody else because you don't know what kind of bloat is in there. Make sure you add the user directive to run as a non-root user. Making sure also your Kubernetes system will support that. Some of them used to not support that, but now they pretty much all do. Sign your images. That's another thing. So when image signing is enabled, by the way, is that basically allows Docker to verify the manifest signature, ensuring that the contents were produced from a trusted source and that no tampering has occurred, right? So you can use a dynamic emission controller that will actually only allow you to launch an image that has been signed, right? So there's a couple of repositories, one of them produced by IBM, not Red Hat, but actually IBM, that will actually allow you to put in a process against the emission controller in Kubernetes. The emission controller, by the way, is an optional kind of policy enforcement engine that you can turn on that will allow you to prevent things from happening or allow things to happen based on certain conditions. So you can actually make it so if the image isn't signed and verified by an authenticated party, it won't actually launch the image in question. Pretty good, actually. There is a EKS best practices guide for security, by the way. Let's see. I'm pretty sure it's under aws.github.io, but let's go take a look. Oh, God. Wow. That's a lot, actually. Huh. Anyway, under EKS distro, they redesigned that page recently. That really caught me off guard. There is an EKS best practices. Hold on. EKS best practices. Hold on a second. AWS EKS dash best practices images. Oh, is that it? This is the best practice guide. I'm not sure exactly what's going on with this particular thing, but yeah, interesting. Huh. Here we go. All right, that's what I needed. All right, so this is the EKS best practices practice guide. I'm gonna post this out in the chat. Sorry that you went on me with a little weirdness there. This thing talks about the guide, introduction, security, cluster auto-scaling, reliability. There's a beta on Windows containers, right? So this guide, I don't know when the last time this guide was written to. It seems to be updated on a fairly regular basis. But this is the best practice guide for security. So it'll go through pod security, multi-tenancy, detective controls, compliances, the whole 9 yards. So if you don't have this link, this is probably a better link here, actually, then this is the place to go. This will help you with image security and Kubernetes. Good, that's useful. All right, so in addition to all the things you can do with the container, other things to think about as part of that whole process is chaining run statements together to make sure the layers are a little flatter. Make sure obviously that you're cleaning up any caches or lingering leftover files. You can also use language specific and application specific base images to reduce layers, right? And then making sure, again, like unnecessary files are deleted, right? Here's an example of a multi-stage build where you're actually sourcing from Golang Alpine to actually like build and copy source set of working directory update certificates, and then using that kind of setup from scratch to build a container using the SSL certs and setting up the binary. So notice the difference in size, right, between hello full and hello scratch. ECR, by the way, will support scanning with Claire, which is something that we talked about before. Claire is something that was published by Quay, which is a company that got bought by Red Hat. There we go. So Claire, right? Use releases, that's funny. This is the static analysis of vulnerabilities in application containers. So just in case I hadn't posted that before, that's the open source kind of static analysis scanner. When you turn this on inside of ECR, it will actually use Claire to basically scan for known vulnerabilities. There's not a lot of control over that thus far, so it uses the standard rule set. It will basically match against known CVEs that are released, like for apt or GCC, like you can see options here, for example, as far as severity. And so those are some really good options. So between the guides and Claire and using Dive to peel back your layers, there's some great options for signing images, shrinking images down, keeping the footprint small, running those alternate users. There's a couple of different options here that you can follow as it relates to improving security on EKS. Now, how do you improve host and network security, right? So you can use an OS optimized for running containers, be immutable with your infrastructure, minimize access to nodes, deploy the workers on private subnets, which is something we've talked about several times. And then you can use Amazon Security Service, Amazon Inspector, which is actually a virtual machine scanner, to basically assess hosts and just see how they're doing. So, and then using things like Session Manager, like that can also like minimize access to hosts, which we've been using in class quite a bit. You can also, by the way, enable network policies, right, using Calico, which I think is originally built by a company called Tigera. So Calico enables network policies on your CNI, basically. So a Calico node agent is deployed on each node as a daemon set, and it can route information using the standard kind of BGP protocol. And so by aligning that VETH naming convention with Calico, like the VETH being the virtual Ethernet interface, the Calico node on each host knows which VETH belongs to each container, and it can create policy rules on each container's interface in the Linux kernel using IP tables and IP sets, right? And so all the traffic that goes in and out of those pods can have these network security policies applied on them to restrict or allow traffic in based on Kubernetes restrictions and not just AWS restrictions. So it basically allows you to implement tenant and network isolation. It does cover both inbound and outbound traffic. You assign network policies to the particular pods, and you can adopt a zero trust model that says, look, nothing is safe. Encryption from end to end, right? Only route through these particular paths. So I don't know why the cat and the ball of yarn are there. That might be Calico's, I think it's Calico's icon, actually, not Tigera's icon, but Calico. Here, you've got a network policy kind that's been added as a custom resource definition inside of Kubernetes. Notice that the name of the policy is default deny, the namespace is web, right? And what it does is that this is going to run as a daemon set in the kube system namespace. And you can, by the way, employ it with the VPC networking or deploy it in its own overlay network. Either one is fine. In this example, Calico is actually going to work with the VPC networking. And so it's going to basically restrict the web space so there's no egress or ingress for that pod in the web namespace from any source. Obviously, this is secure, but it doesn't really allow the pod to function because there's no ingress or egress, right? It can't even talk to other pods, so that's not super useful. Now, if we change it to say, look, now we've got a backend policy, right, that opens the web app backend pod to the front end Nginx pods. So the workloads can now communicate, but they can't, there's no outside connections, right? That's still not allowed. And so notice it says ingress from any app that matches Nginx. And then to take this a step further, now we can say, look, Nginx, you can receive ingress from any port as long as it's port 80. I mean, any IP address as long as it's port 80. So we've added a subsequent set of policies that kind of like combined control who can access what on the pods, right? So now external traffic can reach the front end service, but it can't get to the back end pod, right? Which is typically desirable, right? So Calico can be used in addition to other kind of security features like with AWS and Kubernetes. Like for example, you could restrict firewalls, right, to that system as well. So, but Amazon does advocate a defense in depth kind of policy. So like, having a host-based system in addition to the network-based systems is desirable from Amazon's perspective. Okay, any questions about any of these recommendations? Making sure you deploy them on worker nodes, treating infrastructure as immutable, using approved AMIs that are designed to host containers, and then using Calico to kind of like manage IP tables, IP sets on your hosts. Okay. All right, let's talk about managing secrets. So obviously we know secrets are for sensitive information. We've talked about this a lot. Different from config maps, right? So although ideally you don't hard code credentials into a Docker file, your containers obviously need to be able to pull information. This is where secrets come in, right? And so, secrets can be centrally managed, they can be rotated. And typically there's a secrets management service, if you will, that like defines single use or time delimited keys to an individual container. And it's recommended that you pull them to a centralized location and try not to use environment variables, because environment variables can't actually appear in log files, whereas if it's mounted off of the file system, it's not going to show up, right? So what can be stored as a secret? Well, anything that you consider sensitive, right? So, basically anything, any string, alphanumeric string can be stored, right? Here's a Kubernetes secret. Notice the kind is secret, the name is my secret, the type is opaque. Notice that the data here is a username and password, and that's it. If you get the secrets, you can't see the secret, but you can see that there's 2 pieces of data in there. Now, one thing that's worth kind of peeling back is with Kubernetes.io, which actually we haven't been here for a second, have we? Let's go take a look at this. We're missing the documentation side. I know we are. If you go out here and look at secrets under Kubernetes, one of the things you'll find is that there's a couple of different types of secrets. Notice that we did opaque, which is just a user-defined piece of data. We saw another secret, which was this account service token, which was actually linked to a service account. There are other things like Docker config files, config.json, credentials for basic auth, SSH authentication, TLS, or just a token for bootstrapping. So I just want you to see that, because most of the time we use opaque, but there are other secrets that can be stored inside of Kubernetes. They are typically system defined. So, and opaque is pretty much the default. So otherwise, the rest of these you can read at your leisure. but you've already seen examples of the service account token secret already. All right, so inside of pod spec, by the way, here's a specification. They are defining an environment variable that's actually pulling from a particular secret and key. In this case, it's a secret name, secret underscore username. They typically don't recommend that you do this because those environment variables can show up actually inside the log files. It's actually recommended that you actually mount these as volume, like references inside your pod, and just pull from the file that's being mounted. In addition to secrets, you can add an additional level of encryption. Like, for example, all the etcd volumes that are used by Amazon EKS are encrypted at a disk level using managed keys. Those managed keys come from KMS. KMS is the key management service inside of AWS. So you can actually further encrypt Kubernetes secrets if you want with the key management service, because remember, by default, Kubernetes secrets are just base64 encoded. You can also import keys from another system into KMS and use that key with the cluster without having to install additional software. Yeah. So here's an example of how you can actually use KMS envelope encryption for your Kubernetes secrets. So let's say here a user actually creates a secret. It's going to get stored in etcd, right? So what's going to happen is that the Kubernetes API server in the control plane is going to generate a data encryption key locally to encrypt that key. It's going to encrypt the plain text payload in the secret, and so the control plane is going to have a unique data encryption key for each secret, and the plain text data encryption key is never saved to disk. What will then happen is that data encryption key in red, the one that it's actually using to like scramble up the secret so nobody can read it, it's actually then going to basically call KMS to encrypt that data key with what's called the customer master key, which sits inside of KMS. This key, by the way, is the root of all other data key encryptions, right? So the CMK actually runs on hardware security modules, and what's going to happen is that the API server is going to use that customer master key to decrypt the DEK, and it's going to also cache the base64 of the encrypted DEK, so it's going to save it as well. And then the API server is going to store this like encrypted secret inside of etcd. So if this needs to be revealed to a pod through a volume, it's going to do the reverse, right? It's going to take that data encryption key that it got, the secret that's in etcd. It's going to use the CMK to like decrypt it, right? It's going to to uncrypt the data encryption key, and then it's going to use the data encryption key to then unencrypt the actual secret data. So the customer managed key is what's used to unencrypt the data encryption key. The data encryption key is then used to unencrypt the actual secret data. So that way there's multiple data encryption keys per secret, but there's only one CMK. There's only one customer managed key in this particular environment. And so in order to get that CMK, you've got to go back to KMS and grab it, but the data encryption key is stored in memory, like with the secret. The secret, by the way, is actually stored encrypted in etcd. In the event that, by the way, something is lost here, it'll actually retrieve the data encryption key. Oh, hold on one second. Yeah, so it'll actually retrieve the data encryption key from disk if necessary in order to actually undo the secrets. Sorry, I was hearing a lot of background noise. It was just my son. So this is how you can use KMS and the customer master key to create data encryption keys that you can use to encrypt secrets. And then you can keep the data encryption key and an encrypted version of the data encryption key and the encrypted secret on the system, and then pull them out by grabbing the customer master key off of the KMS modules. So here, you first have to create a customer master key for Amazon EKS to use and export the ARN of the key. So the ARN is the Amazon resource name. And once you export that out, you create a new cluster, which is not uncommon actually. And then in the cluster creation file, you'll actually put the secrets like master key in there. So if we were to look at the EKS CTL file, the YAML file, you would see that encrypted key listed inside. All right, any questions about security options for secrets or for encrypting keys, any of this? Okay. Now let's check one. What is the default behavior for Kubernetes secrets in Amazon EKS? It's the same as it is, by the way, for Kubernetes in general. Are secrets not supported? Are secrets encrypted using AES 256? Are they encoded in base 64 and then stored in etcd on an encrypted disk? Or secrets by default, are they encrypted with the customer master key? What's the default behavior?
See,
C. Secrets by default are encoded in base encoded in base 64, which by the way is the default Kubernetes behavior. And then EKS default is that it's stored in an etcd that's actually on an encrypted volume. That's an EKS default. By default, etcd doesn't like encrypt the disk of the node that it's running on. It can't actually. So the default answer is C. Good, Jarvis. B actually could be a good guess because Amazon tends to love using AES 256 to encrypt pretty much everything, but that's not what happens here. All right, our focus here was to talk about ways to improve container image security, Kubernetes security, Kubernetes networking security, node security, and then just, kind of like general security additions such as using secrets, using envelope encryption for storing your etcd data. And I posted a bunch of links from everything from Claire to Dive to the EKS best practices guide. So I hope that gives you a good little primer around some things to consider to improve the security of your EKS cluster. Any questions about any of this at all before we move on to our last lab of our 3-day period? Awesome. Okay. So here we are securing EKS, right? So we're going to do some messing around. That's the official technical term for labs. You can do some messing around, right? Where you're going to use IAM and RBAC, Kate's RBAC, right, to basically manage cluster access. You're going to manage some APIs, enable an audit trail, and then do some network policy enforcement. And so if we look at the lab specifically, assuming that Michael can find his Firefox window, is that if we open this lab up, that was lab 5, we're on lab 6 now. Wow, once again, hold on. Oh, interesting. It says there's a couple more pre-warming. Hopefully that saves you some time. What we're going to do is that if we look at lab 6, again, bash and host, right? Then managing the cluster using IAM, specifically the AWS auth config map and RBAC. Then we're going to manage some AWS APIs. And you're going to actually hook an OIDC provider. So you're going to use EKS CTL to associate an IAM provider, which is going to do like 4 or 5 steps for you, right? You're going to verify some of those steps. They're going to enable an audit trail for the EKS control plane. And then you're going to do some network policy information, specifically with Calico, which we just talked about. Okay, that's it. So typically an hour is allocated for these labs. It is 3:30 right now. So you get an hour to kick this out. Let's see. Let me just make sure that I'm good on that time. Yeah, it's 60 minutes. Yeah, absolutely. So you get an hour to run this lab. So go forth. Go ahead and click your Start Lab button. If it says provisioning resources, go take a break. right? We only have another half hour after this, so we've definitely got time to cover that last half hour and actually do a little bit, just a quick training prospectus. So if it says provisioning resources, go take a break for whatever time it says, because we haven't taken a break yet this afternoon. Otherwise, oh, go ahead.
So if it says provisioning lab resources, should we end the lab and restart it whenever?
No, don't do
leave it
that.
running? Okay.
Yeah, you will actually extend the time of your lab if you do that.
Okay.
So yeah, it'll actually reset and it will start with a green lab that has no warmth attached, like it has no pre-provisioning attached to it.
Okay.
Yeah. So it basically just eats a pre-provisioned lab and then throws it away. So yeah, so make sure you don't do that. Just like sit there and let it finish. By the way, these have been running for a second, so I'd be shocked that it says 3 of the labs are pre-warmed. There's only 1 left. It looks like a couple of you have your labs going. Of the ones that have, do any of them say that it's like 20 minutes or 10 minutes or 15 minutes for provisioning? Okay.
It's just provisioning.
Yeah, that usually means it's pretty close to being done, because if it was a longer time, it usually says something. But if it does say provisioning, go take a 5-minute, 10-minute break and come back. It should be ready to go. But it looks like most of these labs, there's 3 more apparently pre-warmed and ready to go. So you should be pretty good. All right. 3:30 now, check in about 4:35, about an hour. I'm here in case there's any questions. But if it says provisioning, maybe go take a 5 or 10-minute break and come back and then pick up the lab from there. Speaking of which, I think I'm going to go take a 5-minute break. I'll be right back. Okay, so let me turn on some screen sharing as well, because that's probably going to be useful. It's no good if I just don't share, if I don't share my screen. So let's talk about managing Kubernetes version upgrades. So we just talked a bunch about security. You got Calico, you got RBAC, you got that whole piece of the like integration between the OIDC provider, between IAM and everything else, basically. So we're going to talk about upgrading, because this is probably the other kind of very significant task that you're going to be doing, other than adding and removing nodes and updating node groups and permissions and around security and whatnot. This is the other piece that's really significant. So this only got 3 different components, relatively short, but one, planning for an upgrade, upgrading your Kubernetes version, and then the different EKS platform versions which are associated with the Kubernetes version. So the first thing to do is that if you're going to do an upgrade, just make sure that you read the documentation thoroughly, right? So understand what the impact is to perform an upgrade. Obviously it's identifying who's going to do it, making sure that you have a very clear set of procedures, right? But between the Kubernetes documentation and the AWS documentation, who's going to do contesting? Who's going to do testing? What's the strategy we're going to use? Who's going to do all this? And then assessing the impact to your environment. What's the potential impact? So does your environment have enough resources? Is there IP space? What's the desired strategy, right? Is it a rolling update with 25% down? What are we talking about? So that's the first piece, is just think about who, what, when, where, and why when it comes to upgrading and what the impact's going to be. Now, the AWS and Kubernetes has release notes, obviously, on the kube side, and of course the upgrading Kubernetes, right? The documentation is very comprehensive and very clear. If we go take a look at the EKS user guide, which by the way is just as simple as typing in EKS user guide, right? That will literally take you to the documentation page for EKS. So for example, this is the latest user guide. You could just go to just EKS in general. Here's the API reference. Here's, by the way, there's a link to the EKS workshop. That's pretty cool. I haven't seen that before, right? And then just click into the user guide, and what will happen is that then you'll get access to all the documentation. If you want to stick with it in HTML format, oddly enough, it automatically does that by default. And you can get to see like how things work. If you want to see the table of contents, just click the bars over on the left-hand side, and this will go through all like the different pieces. So here, by the way, is creating cluster, updating cluster, including things such as the kube version and the EKS platform version. So just because they enable you to use a version of Kubernetes doesn't mean all the features are enabled, right? And so, for example, if you look at 1.2, the Kubernetes version is 1.20.4, and there's only, at least here, there's only one platform version. But you may notice that when we were running 1.19, there was actually 4 platform versions. And so, for example, different things were enabled, right, in different sections. So most of this was actually security fixes. But sometimes there are certain APIs, like emissions controllers, that are enabled as a result. So this looks like extended resource toleration was enabled. Volume claim resize was enabled. I think that was in 1.18 as well. But regardless, if you're looking for a feature and you feel like it's missing in your cluster, it's probably because it hasn't been rolled out into an EKS platform version. So now, updating a cluster was the main thing that we were talking about. So this walks through all the steps, right, to do this, including getting the pod security policy, any other DNS config maps, anything else relevant for your rollout, including your EKS ETL versions and whatnot. So make sure you read the documentation. The other thing is that what team's going to be responsible, what's the test environment, what is all the criteria. So the who, when, where, what, and why, from how to get from A to B, from version to version, and the impact upon the resources you're trying to keep running. So now, when you go to upgrade your actual version, just to be clear, minor versions are controlled by customer. So patch versions are automatically applied to the control plane, and they are not automatically applied necessarily to the nodes, right? So new versions are going to basically implement significant changes. So the difference between 1.16, 1.17, 1.18, 19, 20 is significant. Kubernetes tends to maintain 3 versions, like minor versions, active at any given time. AWS maintains 4 to 5. It just depends on what stage AWS is in. But AWS will maintain 4 or 5 at any given time. Here, like you can see the Kubernetes release cycle, which tends to be fairly aggressive. Like in 2020, right? It looks like they released at least 3 major versions, and that tends to be standard. Of the ones that are officially supported by Kubernetes, it's usually like the last 3 once the leading edge one gets out of beta, right? They have an aggressive release schedule. It's usually every like 3 months or so. The project maintains release branches for the most 3 recent minor releases. And so, like, for example, Kube's 1.19 is going to receive about a year of patch support. Kube 19 and older received about 9 months of patch support. So, this is provided by the CNCF. And if this changes, it's going to come from the CNCF. So it's not the support, for example, that AWS provides for EKS. Amazon EKS support for new Kubernetes versions follows a different schedule, which you'll learn about a little later in this module, right? But Amazon's going to support 4 rotating versions at a time. So when they move to a new version and retire another version, like they'll go to 1.20 and they'll retire 1.15. They'll go to 1.21 and they'll retire 1.16. So they'll always maintain a scope. And I think they expanded it because I think it's 5, right? I think people used to say 4, but I think it's 5 that they maintain. And actually, that looks like 5 right there. So, very confusing. So 3 from Kubernetes, but from the CNCF, Amazon will maintain 5 versions available for you to consume inside EKS itself. Now, when you want to upgrade your clusters, you have to identify which dependent components will also need to be upgraded. If you have Calico or add-ons that you've put in, like core DNS and whatnot, these are also going to have to be upgraded. Now, some of these are also sometimes these are pretty core components, right? Even though they're listed as add-ons. but you're going to need to upgrade those as well, including like your EKS CTL, your Kube CTL is going to have to be the latest version. Like all of that needs to be considered. Everything that touches the ecosystem is going to have to be looked at. After you figured out all the dependencies, there's an order for the upgrades that has to have to happen. And then you have to basically plan for any API deprecations, which is really weird because the Kubernetes and Docker community are super aggressive about deprecating APIs, which in some ways is awesome, but that's usually something that you don't do actually, at least in the production application space. But I've literally had them take flags out from underneath me in a release. And I'm just like, what happened to -D? Oh, it's gone. Anyway, minor like releases when you go to like a 1.16, 1.17, 18, or whatever, like the middle number releases, those tend to offer API changes. Like patch releases don't tend to make any API changes. So, so you're planning to upgrade your cluster, you got to identify all the agents that have to be compatible with the new cluster version, right? So for example, nodes have to be updated as well to the new control plane version. Any operators or services like Flux, Core DNS, mission controllers, Calico, all that needs to be updated to handle the new version. And some of the agents may require updating, like the kubelet and the kube proxy as well. Amazon releases AMIs of these nodes that are bottle rocket based that you can actually just pull in. And they're literally labeled 1.20. whatever, 1.19.4. Like they're labeled pretty clearly. For Fargate, it's a little different. All you need to do is recycle the pods, right? And then what will happen is that the kubelet that's in the micro virtual machine will just automatically update to the latest version. So example, you would recycle the Fargate pods so that their kubelet version in this particular case would go to 1.16. Typical thing that happens first is the control plane is updated to maintain backward compatibility, but also to go to the new version. All the associated tools that manage the code plane are actually updated first, then the control plane, and then add-ons for the control plane are updated, and then the data plane is updated. That's typically the way it's done. You can do it one node at a time, or, well, actually, there's really only one node at a time. I don't know that we do it in mass unless you're willing to suffer disruption. So, for example, notice that like here, for example, all the version 1, beta 1 app versions were retired. So you have to like convert everything to apps/version 1 instead. Notice that, like, what was this? This is the 118 release notes, right? By the way, notice that a bunch of stuff came out of beta and went to app version 1, and then networking policies actually went to networking.case.io/version 1, and PSPs under beta went to policy_version 1 beta 1. Right? The service annotation for Azure, where apparently it does some kind of disable TCP reset on an Azure load balancer, that's removed. So those are the kind of things that you're going to find out in the release notes that are probably applicable to your different objects, your resources inside Kubernetes. So you do have to read the documentation, but typically it's tools first, then the control plane, then any add-ons to that have been added on to the control plane, and then the data plane, and then any add-ons, of course, that have been added there as well. So what happens? Like when a new version is available in EKS, you click, hey, upgrade, what happens with a managed service like EKS, right? Because it manages the whole process of upgrading the control plane, but what does it do, right? You just click upgrade and it just goes. Like what happens? So basically what happens is on the back end, invisible to you, it launches new API server nodes with the upgraded version to replace the old API server, right? And I say nodes, they're pods, right? And so AKS is going to perform the standard infrastructure and health checks just to make sure that the API servers are linked in and taking traffic. If any of the health checks fail against the API server, it's going to revert it back and your cluster remains on the previous version, right? No running applications are touched because there's nothing like for it to do. So your cluster is not left in an unrecoverable state. And by the way, EKS regularly backs up all managed clusters, and so it will restore them automatically if necessary. So To upgrade a cluster, by the way, AWS does require at least there to be about 3 free IP addresses from the subnets that were provided when you create the cluster. If the subnets do not have available IP addresses, then the upgrade is going to fail. Additionally, if any of the subnets or security groups that were provided during cluster creation have been deleted, the cluster process is probably going to fail. EKS, by the way, does not modify any of your nodes or any of your K8s add-ons when you upgrade a cluster. You have to do that yourself. It literally only upgrades the control plane components. So before upgrading the cluster, you might want to upgrade any nodes to your cluster's current pre-upgrade minor version if the following condition is true, meaning if your nodes are more than 1 Kubernetes version behind and you decide to upgrade your control plane, you want to get them to within 1 version of your current control plane before you go to the next version of control plane. So just so you know, upgrades have to be sequential. You have to go to 15 to get to 16. You have to go to 16 to get to 19. And then you have to go to 16, 17, 18. Like, you have to follow the upgrade path. You can't just leapfrog cluster upgrades, at least not as a standard. So if your nodes are 2 versions behind your current control plane, you want to catch them up to at least 1, possibly 2. Like catch them up to the current level. Things are just going to go better if your nodes are actually at the same version as your control plane. Go figure. By the way, after your cluster is upgraded, you can update your add-ons as needed, right? Here, by the way, it says, hey, we got a new version available for this cluster. Click, right? It also says that there's new AMI versions released for your node groups as well. So that basically tells you that both your control plane and your data plane have updates available. This is 1.16 on EKS version 1 of 1.16, right? And so just note, if you want to go from 116, like let's say to 119, you got to go 116 to 17, 117 to 18, 118 to 19. Again, you can't skip. Just want to make sure that's super clear. You can use EKS ETL to initiate an upgrade in the cluster, right? It will go forward a version, right? In this case, it's going to push it to 1.17 if you actually use the EKS command. How do you upgrade nodes? Well, if you upgrade nodes and you're using self-managed nodes, then you're going to basically have to push those images out yourself. So you're going to have to grab them, push them and provision them just like you would, right, any other EC2 instance where you're managing the whole thing. With managed node groups, you can actually upgrade the managed node group just by saying, I'm ready to upgrade, right? And so if you're using a managed node group, AWS will do that for you, or you can use the EKS ETL command. Both of them is actually just doing it for you. With Fargate, all you need to do is restart your pods. And by the way, it'll do that naturally. If you lose a replica and it restarts it, it'll just upgrade it to the latest version. You can also, by the way, start a new managed node group with the new version in it and just roll all your pods over there as well. So there's ways to do this without suffering a disruption in any way, shape, or form. So when you do the nodes yourself, you got to make sure that that you are just planning and running the node upgrades intentionally, making sure that you're tracking against any add-on changes or any kind of breaking changes in the particular version of Kubernetes against your applications. You can run a service called AWS Config, which tracks configuration changes in your environment to make sure that you're not run olding versions, right? My recommendation is create a new node group, provision that node group, and then just roll everything over to that node group and retire the other. It's just going to be easier, especially if you have applications with multiple replicas. Then you can just point everything over to that node group, right? Assuming you have IP space for that, which hopefully you should. Remember, most of the IPs are consumed by the pods, so as pods are moved over, your IPs move over as well. So you only need enough IPs actually for the host plus the 3 for the upgrade. So don't worry about running out of IP addresses. As a pod is stopped on the old node group, it'll start on the other node group. And so and the IP address will get assigned. So you won't get flooded with double the number of IP addresses. It will actually retire them and pick them back up. Oops. Hold on. All right, considerations, right? So when you're doing a rolling upgrade of your self-managed nodes, just remember that clusters use a large amount of IP addresses. Make sure you have enough for any new nodes that you add, right? And be aware that your pod disruption budgets may prevent you from rolling things over. So make sure that they're set in a way that will actually allow you to move like one or more pods over, just depending on the density of how many systems you have to upgrade. So you got to think about this kind of thing kind of relatively intentionally. Kubernetes, by the way, has commands to safely drain a node while respecting the pod disruption budget. We've seen some of those pieces. Let's see. I think there is Kubernetes document on this. No, let's go back to documentation. Yeah, thanks. That's weird. Why didn't you go to Kubernetes documentation? Safely draining a node. There it is. So this, if you ever need to safely drain a node, this is a great little task, like using kubectl drain to basically drain the node of all pods, right? And then you can uncoordinate once you're done, right? So there's some options there. For new node groups, by the way, you might want to suspend scheduling on the old ones, consider the impacts, right, for the large node groups, and migrate one application or one kind of deployment at a time to reduce risk, right? There are tools like Flagger, for example, which will greatly reduce the risk of pushing one application. It'll basically move one application, one pod at a time into a system, and the Flagger repository is on Weaveworks. So Flagger. I used to think that I didn't actually have a good memory, but I feel like I'm pulling a lot of this stuff from memory pretty well, actually. Anyway, this is Flagger. Flagger is a tool that allows you to automate the release process running on Kubernetes. So Flagger can actually implement several kind of blue-green A/B testing canary using a service mesh, right? Or an ingress controller like an Nginx or whatever for traffic routing. Traffic, by the way, which is listed here, is a great little traffic is so good. I don't know why I didn't mention this. Traffic is awesome. Not only does traffic have a cool mascot, but this is basically a great little cloud traffic proxy mesh. It basically will allow you to redirect traffic really easily. It's actually a lot easier to use in many cases than Istio or even AppMesh. But anyway, did I paste the Flagger one? Yeah, so this is Traffic. I'm gonna post that out there. Traffic is a great little product that I remember starting using in 2018. And that's a great little alternative to service meshes, but it also gives you ingress controllers. So Traffic's a great little ingress controller that has a bunch of service mesh type qualities to it. Yeah, so to use Flagger, they call it Flux CD now. But use Flagger if you want to control, do some more control around what you're doing with your Kubernetes deployments. Let's see, in migrating to a node group, by the way, you launch the new node group, right? In this case, you'll stop scheduling on the old node group, right? Then you'll taint each node, which will slowly start to move everything over. And then, node group A can just go away. So if you're doing this kind of provisioning in CloudFormation, you can just start a new CloudFormation stack, make sure that RBAC is set up for the new nodes, and then just push everything over to the new set. And that's just, it really isn't that hard. It's just it requires just some care and feeding to watch. So for example, you could scale up the deployments to 2 replicas and force them to run another one on the new node, or double the number of replicas and then retire the other one. So that's also another strategy. I typically just drain a node and it forces it to run on the new stuff after I've blocked scheduling on the existing nodes. By the way, if you wanted to get it so that you could not schedule on a node, would you use labels, affinities, or taints to do that?
Probably taints.
Taints. Taints are the easiest. Yeah. All right. Everything, in this case, everything's moved over. Now for a managed node group, so that was all self-managed, right? That was all self-managed node groups. For a managed node group, first you want to disable the cluster autoscaler. That's the first thing. Stop that thing, right? Make sure that's not running. And that includes the cluster proportional autoscaler as well, right? And so let's see, select the managed node group you want. Just click on update, which is usually an option inside the compute function. And then what it will do is it'll basically say, okay, what do you want to do for the update strategy, right? And so in this case, do you want to do a rolling update? So this, what a rolling update does is if you had a pod disruption budget that says, look, I can't have less than 2 pods running at any time, it's going to respect that, right? And so if AWS, if EKS is for whatever reason unable to gracefully drain the pods, you want to use the rolling update to just respect the pod update, the pod disruption budgets. Now, if you just want to do a force update, this one just forces a node restart with new options, right? And so it doesn't protect the pods from disruption, right? It just basically forces the nodes to evacuate and restart somewhere else. This will disrupt running applications. If you have multiple replicas, it's probably not that big of a deal, but if there are sessions in flight, they will be lost. So, and you can just run an EKS CTL upgrade node group, just name the node group and name the cluster, and it's just gonna go. And that's it. By the way, for Fargate, the only thing you need to do for Fargate is just restart your pods. That's it. To get them to update the micro virtual machines. So I don't know why they don't talk about that, but Fargate requires a restart. Questions about either self-managed upgrades or managed node upgrades? Okay. And the last kind of like pieces we're going to talk about is the EKS platform versions. So this defines which Kubernetes minor versions and the particular features of those minor versions are supported. So it will enable a new API server and it's automatically upgraded by EKS. So for example, Kubernetes isn't, it's not like EKS is not going to upgrade your Kubernetes version, but it will upgrade the flags that are available or portions of this new version that are available for use. So just know that these will be done automatically for you, and they do not disrupt your use of Kubernetes. They just enable feature flags inside. They don't disable feature flags. They enable feature flags inside your control plane, right? The one with the leaders and the primaries in it. So the EKS platform version is associated with, but it's independent of a Kubernetes version. So, you know, it'll start at 1 and go to 2 and 3. And I think the highest I've ever seen is 7, right? For example, AWS might need to release a patch for Kubernetes version 9, like 1.19, but it's like not compatible with version 1.18. So that way they can independently upgrade the configuration of these versions without having to worry about crossover and whatnot. So, yeah. By the way, all patch versions are compatible between EKS control plane and node AMIs for a given version. Meaning if it's 1.19, all EKS 1, 2, 3, and 4, everything they do there is compatible with the 1.19 version. And that's true for the control plane and the node, so the data plane as well. So if it's got 1.19 in the AMI and it's 1.19.4, it's still compatible with 1.19.6. So just making sure I'm clear on that. They bend over backwards to make sure there's compatibility. By the way, without EKS doing it, you got to do all that yourself, which is not as much fun as you want it to be. So EKS supports a minimum of 4 versions at once. Typically, I've seen 5. But I noticed it says a minimum of 4 versions. That's the official documentation. So they're committed to having at least 4. If they have 5, then you got lucky because they were caught in transition, right? And so they support Kubernetes versions for about 14 months, right? And that's how long they'll support them for after first being available on EKS. And this is true, by the way, even if upstream Kubernetes is no longer supporting the version. And by the way, AWS does backport security patches that are available. So if like 1.16 is no longer being supported by Kubernetes, which it isn't actually, then AWS will backport patches to 1.16. So they'll do that for you. So other than those security patches, this is exactly upstream Kubernetes. So this is 100% compatible with the distro. The only thing that's not is if there's a security patch that was released for like 1.2.1 and they rolled it in 121, 120, and 119, AWS will grab that patch and roll it back into like 1.17 or 1.18, even though Kubernetes, the CNCF, is not. So they are committed to making sure that for 14 months, whatever version they're running, they're going to keep it up and alive. You can roll back the upgrade, yes. Oh, you mean as far as the control plane? Like, can you roll back the control plane upgrade? You can't roll back the control plane upgrade. You can roll back the managed node upgrade, but you can't roll back the control plane upgrade. Yeah, if it goes forward, it's going forward, right? I mean, Kubernetes maintains backward compatibility, so I don't know if you've run into issues in the past, but I haven't run into any issues with backward compatibility unless they've deprecated an API that caught me off guard. That's happened because I didn't read the patch notes and I should have, but that hasn't happened for a while. Oh yeah, there's the versions. That's probably not far off from what it's off now. Just add +2 to everything. Okay, so knowledge check. What's the recommended method to upgrade Amazon EKS worker nodes to a new version of Kubernetes? Are these managed or unmanaged? Oh, these are self-managed. Okay, sorry, just checking. Are these self-managed? They're self-managed. So if you have if you want to upgrade some worker nodes to a new version of Kubernetes, does Amazon do that for you automatically for self-managed? Do you deploy upgrade pods as daemon sets to each node? That would be cool, but no, that can't possibly even be true. So we'll just scratch B off. Do you upgrade the CloudFormation stack from the node group to use a new AMI, or do you create a new node group using the new AMI and migrate your pods to that new group? What did I say was probably the most preferred method? So the most preferred method would be to create a new node group, move all the pods over, retire the other group, right? That's the most preferred method. So D. You could do most of these except for B, right? A doesn't do that for self-provision, but like you do C, for example, you could update an AMI ID, but that would be pretty disruptive, actually. All right, we're going to do a knowledge check on Kubernetes support. What determines whether EKS supports a specific Kubernetes feature? Is it the K8s version, the Amazon EKS platform version, the properties of a cluster, or the operating system of the worker nodes?
Hey,
Now that determines whether Kubernetes supports the feature. But if Amazon's going to, like the EKS platform is going to support the feature, that's actually, yeah, you're right. You got it. B. Good. All right. What is the minimum category of Kubernetes version upgrades that can remove APIs? Is it a patch version upgrade, which is C? Is it a major version upgrade, which is A? Is it a minor version upgrade? Or is it D? APIs can be deprecated but never removed. Which one of these is it? I mean, since we hit 1, I think the only time we've ever seen deprecation is certainly not with the patch versions, but only with minor versions, right? When we go to 1.17 to 1.18 to 1.18 to 1.19, right? Yeah, so I think it's B. Yeah. Good. All right, so module says, hey, these upgrades require careful planning. using managed node groups or Fargate can greatly reduce the complexity of having to deal with these version upgrades. And the EKS platform versions identify which features in your version are enabled and supported. That's really not a great, that one. Ignore the slide. The EKS platform version determines which features of that version are enabled. So, including patches. That's it. That, my friends, is the end. It is the last. It is finite. It is the last thing that we have to cover. Does anyone have any questions about anything in these last 4 minutes that we have left? Okay. I'm going to post the evaluation link in. Just know that it does us in AWS a great service. I already noted, by the way, a bunch of things, including labs. Thank you, Mr. Khan, by the way, for giving me feedback on the trouble we had. So I did actually email Quick Labs and got a response. Thank you for your participation. And so just know that your feedback is invaluable, because this actually does help AWS scope the class itself. From a training perspective, I am going to reshare all these links on the EKS workshop, which I think you'll find fabulous, as well as the ECS workshop. You may not know, but the ECS has a great workshop, and that's actually a good product. There's also a app mesh workshop. I don't even know if it's called appmeshworkshop.com. And yep, there's an app mesh workshop and the Kate's networking workshop. So I'm going to send you links for every single Kubernetes related workshop that I currently have that's available for AWS. It'll be about 7 links. There's also another one where awsworkshops.io, is that the one? Oh, here it is, awsworkshops.io. This one's tons of fun, because you can actually click on containers and it will hook you in with third-party products like Harness and Sysdig and Weaveworks and Notice EKS. So you're going to get all these links. You'll have all these links. By the way, I'll post this in there, since that one was kind of a surprise. And so I'm going to make sure that you have connections to at least 5 or 6 crazy chunks of EKS and container goodness that you can use. So I hope this workshop's been instructive. I'd like to think that we all learned something. I know I picked up a few things myself as well, just in terms of like process and pieces like that. So that's it. We're done. Thank you for sticking with me for 3 days, and it's been great. Otherwise, the floor is open for questions or comments or anything that you need to share before we close.
No, thank you very much. Good stuff.
Good.
Thank you.
Yeah. Thank you. Reminder.
Go
ahead, please.
Sorry.
After you.
And I just posted one question in the chat about sample templates.
Oh, yeah. Let's see. Hold on. This might be beneficial to everybody. Let's see. What was it called? Cloud-a-Knots, CloudFormation templates. Let's see. It's one of my favorite one. I do actually have Fargate. I think I have ECS stuff, but I don't think I have good EKS ones. Just so you know, I do most of my stuff in Terraform, just because I have to work on Google and Azure as well. I don't know that I have good EKS templates out of the box. I would probably end up searching for EKS CloudFormation. No, you can search all of GitHub, please. Yeah, so there's some people out there. Actually, we'll send this out there. It looks like they do actually have, there's a couple that have EKS, mainly the stacks, EKS CloudFormation, but I have not tested these, so obviously use them at your own peril. But I mainly end up using Terraform. Like tomorrow I'm teaching an EKS and Terraform workshop actually, and I just use Terraform for that. But there are a bunch of CloudFormation ones out there. I just haven't used them in any length. Oh, wait. Oh, this is a good one actually to share as well. So if you haven't seen this website, this is tons of fun. This is called Former 2, and Former 2 allows you to import resources into either Terraform, CloudFormation, or Pulumi templates, and you can actually just add chunks to it as well. Like if you want to add EKS, oh man, where is EKS on here? I think that would be under compute. I don't see it actually. But anyway, you can actually,
In the containers.
oh, is it under containers? Oh, sorry. I realize they keep changing stuff. So for example, if I actually had clusters in here configured and whatnot, you could actually pull those into your template. So if you find yourself like having manually created a resource or someone else created it, you inherited it, Former 2 is a great website to be able to pull information into infrastructure as code. It was started a couple of years ago by a former SRE. I think it was for Google actually, which is kind of interesting. And you can actually import ForGate profiles, add-ons, all kinds of stuff into your, like you can create CloudFormation with this using existing resources. So it's a fun little website. Make sure you only give it read-only access. The guy who owns it seems pretty reputable, but I don't know who he is, right? So I wouldn't give him anything other than read-only access to my account. So cool. I hope that helps, Rama.
Yeah, thanks.
Yeah. Okay, everyone. So 2 days, I'll send you an email. You get a video link, a bunch of training links from me. If there were links that I posted in here, those change all the time. So hopefully you caught them here. If I have the chat transcripts, which I frequently do, I'll usually just attach them if you actually want to go back and you're like, man, Michael talked about this one thing, and you can go parse through it. But I will send the training links actually in a dedicated email. So give me till about Friday to push that out to you. Otherwise, I hope I see you at the next class, and I really appreciate you joining for this one.
Thank you.
Great.
All right. Have a
Thank you
good
so
one,
much.
everyone.
Bye.